Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Before time, before space, there was nothing. Not darkness, not a void in which something could drift. For even darkness and emptiness require a place to exist. It was a nothingness beyond comprehension, a silence so absolute that no thought or word could pierce it. In that great silence before creation, no light shone, no sound echoed. All the energies and forces we now know were dormant or absent, in a state that defies human language. It is the canvas of non-existence upon which our cosmos would one day be painted. What does it mean to be born from nothing? This question has haunted philosophers and scientists alike. In ancient myths, the world emerges from chaos, from a giant cosmic egg or the spoken word of a deity in the void. These are human attempts to grapple with the ultimate mystery, how something, the universe, reality, everything we know, could spring into being when there was no before, no bedrock of space or time. In the beginning of our scientific story, there is a similar mystery. The equations of physics whisper that time and space themselves began in a stupendous moment, leaving no trace of a prior era for us to read. If there was a before, it lies hidden behind a veil we cannot yet lift. One idea is that time itself began with the birth of the universe. Asking what came before might be as meaningless as asking what lies north of the North Pole. Another idea suggests our universe is one cycle in an eternal series, that the silence before the Big Bang was the echo of an earlier cosmos that ended, and from its demise, our own was born. In this view, nothingness might be more like a cosmic pause between breaths, the universe exhaling and inhaling over infinite eons. But these are speculations at the edge of knowledge. What we know is that roughly 13.8 billion years ago, the silence ended. Out of the void, a flash of creation erupted. In an immeasurable fraction of a second, the universe began. It burst forth from perhaps an infinitesimal point, smaller than an atom, with unfathomable energy. All the matter, energy, space, and time that now exists was concentrated in that embryonic cosmos. The nothingness, whatever it truly was, gave way to a fierce and blazing emergence. The universe was born from nothing in the sense that no pre-existing space cradled it. It made its own space, it made its own time. That first moment was not a normal explosion in space, it was an explosion of space itself. Silence was replaced by a roar of creation, though there were not yet ears or air to carry sound. Darkness was replaced by a searing burst of light, though in truth, the infant universe was so hot that light was immediately trapped, tangled with matter. Still, we speak in metaphors because our minds need them. We imagine a great cosmic dawn breaking over an infinite expanse of nothing, heralding the start of everything. In reality, that dawn was everywhere at once, and the expanse itself was just coming into existence. From absolute silence and emptiness came a thunderous birth. In the first instance, the universe was a tempest of unimaginable energy. Time and space had just unfurled, and everything that would ever be was compressed into an inconceivably dense state. The temperature was so high that the known laws of physics melded together. Forces that today are distinct, gravity, electromagnetism, the forces that bind atomic nuclei, were unified in that newborn moment. There were no atoms, no particles as we know them, only a furious blur of pure energy. Then, in a brief flash of less than a trillionth of a second, something extraordinary happened. The universe underwent a growth spurt unlike anything since. We call this moment cosmic inflation. It may have been triggered when one of the fundamental forces, the strong nuclear force, snapped free from an earlier unified state, releasing an enormous energy that drove space to expand exponentially. Space itself expanded at a staggering rate. far faster than the speed of light. This did not violate any cosmic speed limit. Rather, it was space carrying matter along, stretching the very fabric of reality. In that infinitesimal blink, the universe grew from smaller than a subatomic particle to perhaps the size of a grapefruit or larger. To an outside observer, if one could exist, it would have looked like nothing one moment and an entire nascent universe the next. But there was no outside yet, for space itself was young and expanding. Why did inflation occur? What drove this wild expansion? These questions remain on the cutting edge of cosmology. Perhaps an exotic form of energy in the vacuum triggered it, a high-energy state of empty space that suddenly released its energy into the expansion of space. As inflation raged, it ironed out any irregularities. Just as a balloon, when blown up, smooths out its wrinkles, the inflating cosmos became extremely uniform. Any curvature or clumps were stretched thin. Distant regions that could never have contacted each other under normal expansion were, just moments before, intimately close together. Inflation flung them far apart, bestowing the universe with vast size and an almost featureless consistency. Almost, but not entirely featureless. Even in the raging furnace of the very early universe, randomness played its part. The quantum world, with its jittery, unpredictable fluctuations, left faint imprints on the density of that primordial energy. Tiny flickers, slight differences in density and temperature originating from the quantum foam of existence, were trapped and amplified by inflation. As space ballooned, those minuscule fluctuations were stretched to astronomical scales. Where there was ever so slightly more energy in the microscopic chaos, now there was a denser patch of universe. Where there was slightly less, a thinner patch. These differences were unimaginably small, mere 1 part in 100,000 deviations from perfect uniformity. Yet they were profoundly important. In time, those tiny wrinkles in the otherwise smooth cosmos would grow into galaxies, clusters, and great cosmic structures. In essence, cosmic inflation took quantum whispers and made them the blueprint for the stars and galaxies we see today. The inflationary burst was over almost as soon as it began, a fleeting cosmic heartbeat of expansion. When it ended, the energy driving it did not simply vanish. Instead, like a wound-up spring suddenly released, that energy transformed into an immense bloom of particles and radiation. The universe reheated. In that moment, what we typically think of as the Big Bang, a hot, dense explosion of matter and light, occurred. Space became filled with a high-energy plasma, a hot soup of particles. In that newborn fireball, matter and energy were interconvertible. Particles were created and destroyed incessantly. Quarks, electrons, antiquarks, positrons, photons, neutrinos, all kinds of exotic, fleeting particles roiled in a searing broth. Protons and neutrons did not yet exist as bound states. Instead, their constituents, quarks and gluons, swarmed freely. The temperature was on the order of billions upon billions of degrees. Matter and antimatter were being forged in almost equal measure, only to annihilate back into light. For every billion matter-antimatter pairs that annihilated, a tiny bit of matter, perhaps one particle, survived without a partner. That vanishingly small excess of matter was enough to ensure that our universe would not end up empty. It would become the stuff of stars and life. The universe almost became nothing again through mutual destruction, but thanks to that slight imbalance favoring matter, something remained. A few grains of matter per immense volume of energy, the seeds from which all galaxies, stars, and planets would later form. As fractions of a second turned into whole seconds, the universe continued to expand, though at a gentler pace than inflation's mad rush. With expansion came cooling. By the time the universe was 1 second old, it had cooled to billions of degrees and was still filled with a dense plasma of particles and radiation. In that first second, the basic forces of nature settled into their separate identities. Gravity had split off earliest, during inflation. Now the strong nuclear force and electro-weak force had also separated into the forces we know today: strong, weak, electromagnetic. The stage was set for the next steps in cosmic evolution. Amid this churning plasma, something else important happened in those first seconds. Neutrinos, ghostly, nearly non-interacting particles, decoupled. These wisps slipped out of the dense throng and began streaming freely through space, barely impeded by matter. The universe became transparent to neutrinos almost immediately, at around 1 second old. Those neutrinos still travel today as an all-pervasive cosmic neutrino background, a silent kin to the light that would later be set free. They are hard to detect, but they remain one of the surviving whispers of the infant universe. The embryo universe, still less than a minute old, was immensely hot and bright. Quarks had begun to combine into triplets, forming the first protons and neutrons within the first millionth of a second, once the universe cooled below roughly 1 trillion degrees. Now, as time passed the mark of a few seconds, the frenetic particle-antiparticle annihilation ended. Most antimatter had paired off and disappeared in a flash of gamma rays, leaving that tiny surplus of matter. A sea of photons, light particles, dominated the energy content, but there were also countless neutrinos, and a growing number of protons, neutrons, and electrons, the raw ingredients of atoms, though not yet assembled into atoms. As the newborn universe moved from its first seconds into its first minutes, it continued to cool and expand. The frenetic collisions of particles began to slow just enough for new kinds of order to emerge. Around 3 to 4 minutes after the bang, the temperature fell to about 1 billion degrees, roughly 70 times hotter than the core of the Sun. Now atomic nuclei could begin to form. Protons and neutrons, freshly forged from quarks, found the universe cool enough to stick together under the embrace of the strong nuclear force. A second great creation event unfolded in this period. Big Bang nucleosynthesis, the formation of the first atomic nuclei. In the blazing furnace of these early minutes, protons slammed into neutrons and fused. Helium, the second simplest element, began to form in abundance. For a brief window of time, conditions were just right for nuclear fusion on a cosmic scale. Much as the cores of stars billions of years later would fuse hydrogen into helium, the entire young universe functioned like a star, converting the simplest elements into slightly heavier ones. Over about 17 minutes, most of the neutrons in the universe, which are unstable on their own and would decay if left isolated, managed to fuse into helium nuclei, each consisting of 2 protons and 2 neutrons, or a few other light nuclei. By the time this period ended, about 25% of the mass of ordinary matter had become helium nuclei, with the remaining 75% remaining as hydrogen nuclei, single protons. A trace of deuterium, heavy hydrogen, and lithium, with 3 protons, also formed. The universe's initial chemical makeup was set: predominantly hydrogen, a healthy dose of helium, and tiny traces of lithium and beryllium. After about 20 minutes, it had expanded and cooled too much for further fusion. The furnace of the Big Bang's beginning flickered out. At this point, the universe was still an extremely hot plasma. Imagine an extremely dense, opaque fog of charged particles, electrons, nuclei, and photons. It was as bright as the interior of a star, but no light could travel very far. Space was like a brilliant, blinding mist. Any photon, particle of light, that tried to go more than a tiny distance would smack into a free electron and scatter. The universe was opaque, a glowing fog of light and matter tightly coupled. To an imaginary observer floating at, say, 100,000 years after the bang, the surroundings would look like a uniform glow, as if you were embedded in the surface of a star. You wouldn't be able to see through it. The concept of distance beyond a certain point had no visual meaning because light hadn't yet broken free. The cosmos was radiating, but curtained by its own dense matter. However, The expansion continued, and with it came cooling and thinning of that particle soup. Thousands of years passed, then tens of thousands. During this epoch, the energy of the universe was dominated by radiation, light, which kept matter particles flying apart and resisted gravity's efforts to clump things together. But gravity was patiently tugging on the matter nonetheless, and as the universe grew, the density of radiation fell faster than the density of matter. About 50,000 years in, matter took over as the dominant component controlling the dynamics of the universe's expansion. The radiation era gave way to the matter era. This meant that at large scales, gravity now had the upper hand to start drawing matter together into the seeds of galaxies and clusters, though it would still be some time before these structures became pronounced, since everything was still mixed in the hot plasma. Fast forward to approximately 380,000 years after the Big Bang. The temperature had fallen to around 3000 K, about the surface temperature of a cool star, roughly an orange glow. At this point, something profound occurred. Electrons began to combine with nuclei to form neutral atoms. A proton capturing an electron makes a hydrogen atom. Helium nuclei capturing electrons make helium atoms. This process is called recombination, though it's really combination for the first time. With most electrons suddenly bound into atoms, they were no longer free to scatter photons at every turn. The cosmic fog lifted. The universe became transparent. It was as dramatic as night turning into day on a cosmic scale, except here it was a bright, hot fog turning into clear darkness. For the first time, light could travel great distances without being immediately absorbed or deflected. When the cosmic fog cleared, the light that had been trapped was released to fly freely through space. The universe was about 380,000 years old, and this was its first free streaming light, often called the first light of the cosmos. The entire sky everywhere would have glowed with a bright, warm radiance. If human eyes had existed then and could survive the conditions, they would have seen a soft, orange-white glow coming from all directions, like being in the middle of a vast glowing cloud. That glow was the combined light of the hot plasma, suddenly unleashed. As the universe expanded over time, this flash of light lost energy and shifted to longer wavelengths. What started as an intense orange-white glow stretched into a dimmer red, then into the infrared, and eventually, over billions of years, into the microwave part of the spectrum. Today, we detect this primordial light as the cosmic microwave background, CMB, a faint afterglow permeating the entire universe. The CMB is the oldest light we can see, a messenger from the cosmic infant years. It is extraordinarily uniform, with a temperature of about 2.725 K, just 2.7 degrees above absolute zero in every direction. Yet, it's not perfectly uniform. There are tiny variations in its temperature, only tens of microkelvins different, 1 part in 100,000 of difference. These subtle freckles in the CMB are the direct imprints of the quantum fluctuations from the time of inflation, imprinted on the matter distribution when the universe was young. Regions that are a hair hotter in the CMB correspond to slightly denser areas back then. Slightly cooler spots correspond to slightly less dense areas. These differences are only a fraction of a percent, but they are crucial. Over time, gravity will amplify those slight over- and under-densities into the cosmic structures we see today. When we map the CMB, as satellites like COBE, WMAP, and Planck have done, we are effectively seeing the seeds of galaxies and clusters, the universe's baby picture, with a mottling of warm and cool spots encoding the initial blueprint of cosmic structure. So at 380,000 years old, the universe has become a relatively cool 3000 K neutral hydrogen and helium gas, filling space almost uniformly, and it's transparent. The brilliant youthful glow has now faded into a dull red warmth, and then beyond visible light entirely. What followed is a period often poetically called the Cosmic Dark Ages. Why dark? Because now, with the primordial glow gone, there were as yet no stars or galaxies shining. The universe was transparent and dark. The gas was cooling. The light from the Big Bang was drifting outward and redshifting into invisibility. And space was largely unilluminated, save perhaps for very faint glows from atomic transitions or cooling gas. Nothing like the bright lights of stars. An observer floating at, say, 100 million years after the Big Bang would see a black sky. The temperature of the background radiation would be a few tens of Kelvin, so mostly microwave radio waves, nothing to see with eyes. Yet all around, gravity was quietly working on the slightly denser patches of gas, drawing them inwards. Gas was not perfectly uniform throughout the universe. Those cooler, slightly denser regions of the primordial gas, the ones corresponding to slightly cooler spots in the CMB, exerted a bit more gravitational pull. They began to gather more gas from their surroundings. Invisible clumps of dark matter, more on this mysterious component soon, were also drawing gas into their deep potential wells. During these dark ages, the universe was like a calm night where nothing visible happens, but seeds are germinating under the soil. Gravity amplified the tiny variations, slowly but surely, pulling hydrogen and helium into ever-growing clouds and filaments. The distribution of matter started to resemble a spider web, dense nodes connected by filaments, with voids in between, though at this early time it was all still diffuse and no stars had lit up. After perhaps a few tens of millions of years, the largest of these gas clouds, particularly where the invisible dark matter had clustered strongly, grew dense enough at their cores to trigger a new phenomenon. The gas at the center of such a cloud, pulled in by gravity, began to heat up as it fell inward. Kinetic energy of infall converted to thermal energy. Eventually, one critical cloud crossed a threshold. Its core reached temperatures of millions of degrees and high pressure. Nuclear fusion ignited. A huge burst of energy was released from the core, and a delicate balance was struck between gravity and pressure. A star was born, the first star in the universe. In pockets across the cosmos, this process repeated. Wherever a pocket of gas became dense and hot enough, a new star lit up. The first stars were likely very massive, dozens or hundreds of times the mass of our Sun, because without heavier elements, like carbon or oxygen in the gas, it couldn't cool as efficiently, and thus fragments of collapsing gas clouds tended to be large. These first stars burned a bright blue-white, extraordinarily luminous, and very short-lived by stellar standards. One by one, like brilliant blue-white beacons, they pierced the cosmic dark. It was as if the universe saw the light of its first campfires, kindling in a vast, cold wilderness, points of illumination sparking up in the blackness. The era of rionization had begun. Each first star flooded its neighborhood with energetic ultraviolet photons. These photons had the power to ionize neutral hydrogen, that is, to knock electrons off atoms. The neutral gas around each new star became electrically charged, ionized once again, forming bubbles of plasma amidst the neutral background. Initially, these ionized bubbles were small, centered on individual stars or star clusters. But massive stars live briefly. In a few million years, many of them would have died in violent supernova explosions, enriching the surrounding gas with heavier elements like carbon, oxygen, and iron. New stars were born in those same regions, some a bit smaller and longer-lived, thanks to the cooling effect of the newly introduced heavy elements. Over several hundred million years, more and more stars formed, and the ionized bubbles around clusters of stars grew and merged. As the first generation of stars grouped into the first proto-galaxies, their combined ultraviolet glow carved out ever-expanding cavities of ionized gas. Imagine the once neutral universe now being Swiss cheesed by growing holes of ionization. Finally, by around 1 billion years after the Big Bang, nearly all the remaining hydrogen in intergalactic space was ionized again. The universe became transparent to ultraviolet light as well, as the last fog of neutral hydrogen was banished from intergalactic space. The Dark Ages had fully ended. The universe was filled with starlight. During this epoch, the cosmic landscape transformed rapidly. Gravity pulled the early star clusters into tighter groups. These groups merged to form nascent galaxies. The first galaxies were smaller and more irregular than the grand spirals and ellipticals we see today. They often were chaotic assemblages of stars, blazing with the light of massive new stars and the explosions of supernovae. Over time, small proto-galaxies merged to form larger ones. The cosmic web, the large-scale structure of matter, became more pronounced. Filaments of dark matter and gas channeled material into the growing galaxies, while vast voids were emptied of matter as it flowed towards the filaments. Some of the early massive stars likely collapsed into black holes after they died. These could have become seeds for the supermassive black holes we find in galaxy centers today. Indeed, by as early as 700 million years after the Big Bang, we have evidence from quasars observed by telescopes that some black holes of billion solar mass scale had already formed and were devouring matter, shining as intensely luminous quasars. That indicates the assembly of galaxies and black holes was well underway very early. In those first billion years, the universe went from a dark, uniform fog to a web of glowing galaxies. It was a dramatic transformation, a kind of cosmic adolescence full of growth spurts and turbulence. Over the next several billion years, this web of structure became ever more complex and beautiful. Gravity and time together sculpted an immense cosmic architecture. Galaxies gathered into groups and clusters, and those clusters themselves drew together into larger complexes called superclusters. On the grandest scales, matter arranged itself in filaments and sheets, weaving around enormous voids. This pattern is the cosmic web. The web forms as the gravitational attraction of matter draws things together along the path of slight initial overdensities. Galaxies are not scattered randomly. They lie along these filaments. Where filaments intersect, we get clusters and superclusters of galaxies, immense nodes of the web. In between lie voids, vast regions with far fewer galaxies, as if the web's threads outline bubbles of nearly empty space. To visualize the cosmic web, imagine looking at a frothy foam or a network of neurons in a brain. Clusters and superclusters are like the knots, filaments like the threads between, and voids like the empty gaps. One filament can stretch hundreds of millions of light years from end to end. Observations have revealed structures such as the Sloan Great Wall and others that span over 1 billion light years. Chains of galaxy clusters lining up. The largest structures known, great walls of galaxies, huge quasar groupings, approach scales where the word structure itself starts to blur, because on scales above a few billion light years, the universe looks homogeneous. Still, these enormous formations amaze us. For instance, one huge grouping of galaxies called the Bootes supervoid, though it's a void, is so large and empty that if galaxies were peas scattered across space, it would be like an expanse tens of millions of kilometers with only a handful of peas. It's a tremendous volume of space with hardly any galaxies at all, akin to a great cosmic cavern. Within the filaments, galaxies continue to interact. Galaxy clusters, collections of hundreds or thousands of galaxies bound by gravity, form at filament intersections. Our own galaxy, the Milky Way, is part of a small cluster, or group, called the local group, which in turn sits on the outskirts of the Virgo supercluster, which itself is part of an even larger structure, often called Laniakea, a supercluster complex spanning 500 million light-years. Our local group contains the Milky Way, Andromeda, and dozens of smaller galaxies. Laniakea, a Hawaiian word meaning immeasurable heaven, includes the Virgo cluster and hundreds of other groups, all flowing within a common gravitational basin. It is just one of many superclusters in the observable universe. Even within our local group, cosmic evolution continues. The Milky Way and the Andromeda galaxy are drifting inexorably toward each other. In about 4 billion years, they will merge, forming a new, larger galaxy. This will be a slow-motion collision. Stars are so far apart that few, if any, stars will hit head-on. But the two galactic disks will distort and blend, likely forming a big, elliptical galaxy with a new structure. Such mergers have happened countless times in cosmic history, especially in clusters where galaxies are crowded. It's one way galaxies grow and transform. Our own eventual merger is just a small chapter in the long story of structure formation, but it highlights that even galaxies themselves are impermanent, ever-changing. The cosmic web forms a sort of scaffolding that cradles everything that exists within the universe. And remarkably, the shiny galaxies we see, the gas, dust, and stars, are only a small fraction of the matter involved in this structure. There is an invisible component called dark matter that outweighs the ordinary matter by about 5 to 1. Dark matter neither emits nor absorbs light, so we don't see it directly, but its gravity betrays its presence. It was dark matter that seeded the cosmic web. During the Dark Ages, dark matter clumped under gravity. It does not interact via light or pressure, so it started collapsing even when normal matter was still a hot plasma. These dark matter clumps served as gravitational wells, pulling in ordinary gas after it became neutral. Without dark matter, the gas alone might have taken much longer to form stars and galaxies, but with it, structure formation was boosted. Every galaxy sits in a cushion of dark matter, a dark halo, much more massive and extended than the galaxy's visible extent. In clusters of galaxies, the combined dark matter of the cluster creates deep potential wells that hold the cluster together. In fact, observations of galaxy clusters in the 20th century first provided evidence of dark matter. Galaxies were moving too fast to be held by visible matter alone. So one can picture the cosmic web as an invisible framework of dark matter, upon which gas settled and cooled to produce galaxies. The luminous matter traces the patterns drawn by dark matter's gravity. By around 5 billion years after the Big Bang, many of the structures we see today were in place. The cosmic web was well established. Galaxies had matured and grouped into clusters and superclusters. Stars had been forming for billions of years in those galaxies. In fact, the peak of star formation in the universe likely occurred around 3 to 4 billion years after the Big Bang, when galaxies were in a star-bursting frenzy. After that peak, star formation gradually declined as the gas reservoirs in galaxies were used up or heated or expelled by various processes. In fact, around this midpoint in cosmic history, the conditions were ripe for planetary systems like our own to form. Generations of earlier stars had enriched the interstellar gas with heavy elements, carbon, iron, oxygen, etc., forged in stars and supernovae. In one typical spiral galaxy, our Milky Way, a cloud of such enriched gas and dust collapsed around 4.6 billion years ago to form a new star, our Sun, and a retinue of planets. This was possible because at least 9 billion years had passed since the Big Bang, allowing multiple cycles of star birth and death to scatter the ingredients for planets. Our Sun lit up in a relatively quiet corner of the Milky Way, and around it formed a system of planets, including Earth. On that young Earth, formed from cosmic dust and the debris of earlier stars, complex chemistry began to brew in its oceans and atmosphere. By a few 100 million years after Earth's formation, life arose, simple at first. Over eons, that life became more complex, leading to creatures that could look up and marvel at the stars. In this way, we humans are very much a product of cosmic evolution. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in long-dead stars and scattered through space, incorporated into the Sun and Earth, and ultimately into us. Our emergence is an exquisite example of the universe giving rise to organized complexity capable of contemplating itself. While this was happening on the scale of galaxies and life, another, even larger scale drama was unfolding in the background, the expansion of the universe itself. Since the Big Bang, the universe has been expanding, but for a long time, it was expected that this expansion should be slowing down due to the pull of gravity. Indeed, for the first few billion years after the Big Bang, the expansion was decelerating. The mutual gravity of all the matter in the cosmos was putting the brakes on the expansion. Galaxies, though being carried apart, were doing so at an ever-slowing rate. One might have imagined that given enough time, the expansion might even stop and reverse if gravity was strong enough. However, about 6 or 7 billion years after the Big Bang, roughly at the time our Sun formed, something curious started to happen. The expansion began to speed up again. Galaxies started to recede from each other faster and faster. This discovery, made by observing distant exploding stars, supernovae, in the late 20th century, was revolutionary. It implied the presence of a new ingredient in the cosmic recipe, something pushing the universe outward. We call this mysterious influence dark energy. Dark energy is the name we give to the unknown cause of the accelerated expansion. It appears to act much like what Einstein once hypothesized as a cosmological constant, an intrinsic energy of empty space. Einstein originally introduced such a term to allow for a static universe, then removed it when expansion was discovered, reportedly calling it his biggest blunder, not realizing the universe actually does have a similar effect present. Dark energy doesn't dilute as the universe expands. It remains, as far as we can tell, constant in density. As space grows, the total amount of this energy increases, because more volume times the constant density yields more energy. In effect, dark energy is like an anti-gravity pressure uniformly filling space, pushing things apart. For the first several billion years, dark energy was negligible compared to matter. Matter's gravity was slowing the expansion. But as matter spread out and its density dropped, dark energy eventually became significant. About 5 billion years ago, dark energy's repulsive effect overtook the self-gravity of matter in the universe. The expansion, which had been slowing, stopped decelerating and began to accelerate. Small distances, like within galaxies or clusters, weren't affected. Those structures are bound by much stronger local gravity. But on large scales, between clusters and superclusters, the gaps began to widen faster and faster. To picture the effect of dark energy, imagine the universe's expansion as a ball that was thrown upward, the Big Bang being the throw. First, the ball climbs, but slows, gravity's pull. Then, unexpectedly, it starts accelerating upward as if pulled by an unseen force. Dark energy is akin to that unseen force accelerating the expansion of the cosmic ball. Another analogy: think of 2 points in space with a spring between them, gravity, and an expanding rubber sheet under them, space itself expanding. Initially, the spring slows their separation, but if the rubber sheet stretching, dark energy, grows strong enough, it will overcome the spring and the points will fly apart faster and faster. The simplest form of dark energy, consistent with observations, is a true cosmological constant, an unchanging energy woven into the fabric of space-time. If that is the case, then the fate of the universe is a continual acceleration. Distant galaxies will recede at ever-increasing speeds. Eventually, far in the future, distant galaxies currently visible will be carried beyond our horizon of visibility because space is expanding so fast that light from them can no longer reach us. The night sky over tens of billions of years will grow emptier as galaxies vanish from view one by one. Today, dark energy makes up about 68% of the total energy content of the universe. Matter is about 32%, of which about 27% is dark matter and 5% normal matter. Thus, the cosmos, by composition, is mostly this invisible, dark energy. It's astonishing. All the galaxies, stars, gas, and dust, everything we see, is only a trace component. Yet, it is thanks to that small component that we have structure and life. Dark energy, ironically, mostly influences the voids and the eventual destiny. Even now, dark energy's presence is subtle on human timescales. The Milky Way and Andromeda will still collide despite cosmic expansion because they are gravitationally bound strongly enough to overcome expansion at local scales. The local group of galaxies will remain together, but clusters that are not bound to us will drift away. For instance, galaxies in the Virgo cluster, tens of millions of light years away, will recede further. In a few 100 billion years, should any observers be around, virtually all galaxies beyond the local group will have disappeared from view, being carried away faster than light can catch up. To summarize the cosmic inventory and its effect, dark matter provided the scaffold for structure and still holds galaxies and clusters together. Dark energy drives the overall expansion ever faster. Normal matter, atoms, forms the stars, planets, and living beings. Each plays a role in the grand cosmic story. Dark matter pulled the cosmos into a beautiful web. Normal matter lit that web with stars. Dark energy is now pulling the web apart at its largest scales. Time marches forward, and with it comes change. But why does time have a direction at all? We recall the early universe was an extremely hot, uniform state. And now we have a clumpy cosmos and cool expanses. Things have clearly moved from a state of order to increasing disorder. This one-way progress is encapsulated in the concept of entropy. The second law of thermodynamics says entropy, disorder, tends to increase in a closed system. This law underpins the arrow of time. Eggs break, but do not unbreak. Cream disperses in coffee, but never spontaneously gathers back at the top. A piece of paper burns to ash and smoke, but the ash and smoke won't reconstitute into paper on their own. These processes involve increasing entropy, and they define an irreversible direction to time, from past, lower entropy, to future, higher entropy. The universe as a whole began in a state of incredibly low entropy. At the moment after the Big Bang's initial inflationary smoothing, matter and radiation were almost perfectly uniformly spread. Paradoxically, uniform gas is a low entropy state in cosmology because gravity can do a lot of work with it. Imagine a smooth spread of matter that can clump versus matter already clumped into black holes. The latter is a higher entropy state gravitationally. The early universe had very low gravitational entropy, everything spread out smoothly, and not maximal thermodynamic entropy either. There were temperature differences and lots of free energy available. This special beginning, perhaps set by inflation or whatever preceded it, is why there was an arrow of time. The cosmos started wound up, like a clock with a lot of free energy and potential to evolve into more disordered states. As the universe aged, entropy increased. The formation of stars and galaxies might seem like an increase in order locally, but overall, entropy rose because, for example, when a star shines, it produces a lot of thermal radiation, high entropy, out of nuclear fuel, lower entropy state. The light that escapes into space carries away entropy. The net effect of all processes, gravitational clustering, star formation, life, has been to increase total entropy. Entropy is now vastly higher than in the pristine early universe, and it will continue to increase. What is the ultimate fate implied by ever-increasing entropy? It is often called the heat death or big freeze. This scenario is a universe where, on the largest scales, everything becomes uniform again. Not in a low entropy way like the beginning, but in a maximum entropy way. A thin mist of particles and radiation at near uniform temperature, with no gradients to power any process. If dark energy continues to accelerate expansion forever and nothing intervenes, this is the likely end state trillions upon trillions of years hence. Let's trace that future vision. First, over the next few trillion years, star formation in galaxies will taper off. Galaxies have a finite supply of gas to make new stars. Eventually, that gas runs out or becomes locked in stellar remnants. The longest-lived stars, small red dwarf stars, can burn for trillions of years, far longer than the current age of the universe. So, billions of years from now, galaxies will be dominated by long-lived red stars slowly fusing hydrogen. As time marches on, even these will exhaust their fuel. By around 100 trillion years from now, 10-14 years, the era of star formation will officially end. We enter the so-called degenerate era, dominated by stellar remnants. In that far future, the galaxies, those that remain gravitationally bound, like our future Milkdromeda, the merged Milky Way Andromeda, will be populated only by degenerate objects: white dwarfs, cores of spent stars, neutron stars, brown dwarfs, failed stars, and black holes. New stars will no longer be born. The remaining stars will slowly cool and dim. White dwarfs, starting hot, will radiate their energy over billions and trillions of years, turning into black dwarfs, cold, dark, stellar embers. Planets, if any still orbit, will gradually spiral into their stars or be flung out by gravitational encounters over extremely long timescales. At this point, entropy is still increasing. Complex structures decay. Perhaps some hypothetical, incredibly long-lived civilization might find ways to survive around fading sources of energy, but eventually usable energy supplies would dwindle. After many trillions more years, even larger structures start to destabilize. Gravitational interactions within what's left of galaxies will gradually eject many objects into intergalactic space, a process called dynamical relaxation. Central black holes might collect some matter, while other stars or remnants are thrown to the outskirts or beyond. Fast forward to unimaginably distant times, 1019, 1020, up to 1040 years. By 1020 years, most galaxies as we know them may disperse, stars either fallen into central black holes or scattered. Around 1040 years, a number so large it defies comprehension, even protons, if unstable, some particle theories suggest protons might eventually decay, will have decayed into lighter subatomic particles. If proton decay is real, at this point, solid matter dissolves. Planets, white dwarfs, any remaining asteroids or dust, all would literally evaporate into radiation and elementary particles. The universe becomes a dilute soup of electrons, positrons, neutrinos, and photons, perhaps with some lingering protons if they're absolutely stable, and lots of dark matter particles, assuming dark matter is stable and doesn't decay. We aren't sure, but likely it is stable. One might think black holes would still be around as massive reservoirs of mass, even after normal matter is gone. And they will, for a long time. But even black holes aren't eternal. Stephen Hawking theorized that black holes slowly evaporate by emitting Hawking radiation, a very slow quantum thermal glow that causes them to lose mass over time. For stellar mass black holes, the evaporation time is around 10^67 to 10 years. For supermassive black holes, millions or billions of solar masses, like in galaxy centers, the time is stupendously larger, on the order of 10^98 to 10^100 years or more. But given enough time, even these giants will eventually evaporate completely, each ending in an explosive burst of high-energy particles when its mass becomes very small. After the last black hole has vanished, the universe enters its final stretch, the dark era. The temperature everywhere will approach an extremely low value as expansion dilutes any remaining energy. Essentially, what remains is a sparse sea of photons, mostly of extremely long wavelength radio waves, some electrons, positrons, neutrinos, and perhaps some dark matter particles if they haven't decayed, all spread so thin that in a volume the size of our Earth, you might find essentially none of those particles. Entropy is maximized. In a sense, the cosmos returns to a featureless state, not of super-hot plasma like the beginning, but of near-empty cold space. All gradients of temperature or density are ironed out. With no free energy differences, no work can be extracted to power any process. Change virtually halts. This is the heat death, Time would still pass, but nothing of significance would mark its passage. It's a ghost universe, silent, empty, and everlasting, unless some fluctuation eventually breaks the stalemate, which we'll touch on. The arrow of time at that point would effectively cease to matter, because there would be no events to distinguish past from future. The great cosmic drama would have quietly exited stage right. However, this fate assumes a constant dark energy and no new physics intervening. We must acknowledge other possibilities. The universe's end might be more dramatic or lead to a rebirth. One such possibility is the Big Rip scenario. If dark energy is not constant, but instead grows in strength, for example, its equation of state has W1, a so-called phantom energy, the acceleration would become more and more violent. Eventually, even gravitationally bound systems would not hold together. In a Big Rip, first clusters of galaxies would be torn apart, galaxies receding from each other despite being bound, effectively overcoming their mutual gravity. Next, galaxies themselves would be shredded, stars flung out as the space within the galaxy expands faster than the galaxy's gravity can keep up. Closer to the rip, solar systems would unbind, planets would fly off from stars. In the final moments, stars and planets would be ripped apart, and even atoms and atomic nuclei would be sundered in the ultimate blow. The timeline for such an event depends on how phantom the dark energy is. If it were just slightly more negative than 1 in its equation of state, the Big Rip might be trillions of years away, or not happen at all, if it tends asymptotically to a constant. If it's substantially more negative, the rip could happen sooner, though current data suggest dark energy is very close to a cosmological constant, World 1. The concept is spine-chilling, the fabric of space accelerating so wildly that it rips apart anything bound. Matter is literally disassembled by the expansion of space. Most physicists consider this unlikely based on current evidence, but it's not ruled out absolutely. If our current best fit is slightly off, the cosmos might end not in ice, but in a singular crescendo of tearing apart everything. Another scenario, the Big Crunch. This is in a sense the opposite of heat death or Big Rip. It's a reversal of the expansion into a contraction. If, for some reason, dark energy were to dissipate or turn attractive, and if the density of matter were high enough, gravity would eventually win out and pull everything back together. The expansion would slow, stop, and reverse. Distant galaxies would start to approach rather than recede. Over billions of years, what was once an expanding universe becomes a collapsing universe. Galaxies would rush together. Clusters merge into a supercluster, superclusters into huge sheets, and finally all material closes in. The temperature of the background radiation, which had been dropping for eons, now starts to rise again as space compresses that radiation. The dark, quiet cosmos would light up once more as every particle of light gains energy and blue shifts. Galaxies might careen into each other with increasing frequency. The night sky would glow brighter and brighter as more galaxies cram into our observable view, and the heating of all gas triggers star formation, or makes existing stars shine more fiercely. In the far future of a Big Crunch, the universe's scale continues to shrink. What were galaxy superclusters a few billion years before are now overlapping and colliding. Eventually, all matter might coalesce into an extremely dense state. The temperature would soar to star-like or greater levels everywhere, ionizing whatever atoms existed once more. Fusion could ignite in giant bursts as gas clouds compress. Essentially, the reverse of the universe's expansion timeline happens. Clusters of galaxies collapse into blazing quasars, then into massive nebulae, then into a shrinking ball of plasma, then perhaps into conditions similar to the very early universe. If quantum gravity or other effects don't intervene, this collapse could lead all the way back to a state of seemingly infinite density and temperature. Essentially, a mirror image of the Big Bang, sometimes dubbed the Big Crunch. Is that truly an end, or could it be a bounce? Some modern theories speculate that a Big Crunch could transition into another Big Bang. the death of one universe seeding the birth of a new one. In cyclic models, the universe might undergo endless, or at least many, Bang Crunch cycles. Ancient cosmologies, like Hindu cosmology, imagined time as cyclical, cosmic days and nights of Brahma, with universes expanding and contracting periodically. A scientific version might be, after a crunch, all space and time re-expand again, maybe after reaching a singularity, or perhaps never fully reaching infinite density because new physics causes a rebound. If there is a bounce, the astonishing implication is that our Big Bang might not have been the absolute beginning, but simply the latest bounce. Some theorists working in quantum cosmology and string theory have explored models where, for example, our 3D universe, brain, periodically collides with another brain, causing big bangs in a cycle. Others, loop quantum cosmology, find that quantum effects could cause space to repel at extremely high densities, avoiding a singularity and starting expansion anew. If the universe can bounce, what happens to entropy and the arrow of time in such a cycle? That's a tough question. Naively, entropy would carry over and increase with each cycle, which would be problematic. You can't cycle indefinitely if entropy irreversibly accumulates, unless the bounce somehow resets the entropy or disposes of it. Some proposals, like conformal cyclic cosmology, Roger Penrose's idea, suggest that at the end of a heat-death scenario, when the universe is nothing but photons and essentially devoid of scales, it might be possible to relabel that state as the initial singularity of a new Big Bang. Since a universe of only structureless photons has no concept of time or size, it could be equivalently reinterpreted as a new Big Bang state. This is speculative and not widely accepted yet, but it shows how creative thinking is being applied to the idea of cosmic rebirth. There are also other theoretical fates. One is a vacuum decay scenario. Perhaps our current vacuum, the ground state of fields in the universe, is not the true lowest energy state. If there exists an even lower state, the universe could at some point quantum tunnel into that lower state. If that happened, a bubble of true vacuum would appear somewhere and then expand at near the speed of light, converting everything it touches into a new state of being. Within that bubble, the laws of physics might be different constants, particle arrangements. So essentially, it's like a new universe erasing the old one. This bubble nucleation and expansion would be catastrophic, from our perspective, and extremely fast. One moment everything's fine. The next, a bubble of alien vacuum is rushing through you, disintegrating you, Earth, and every structure. And we'd never see it coming because it expands at light speed. It's a wild idea, but certain particle physics models make it a possibility. For instance, if the Higgs field sits in a metastable false vacuum. Current data suggests it's not highly likely in the near term. If it can happen, it might be trillions of years away or more. Or maybe it's truly stable and won't happen at all. In any case, it's another way nothing, or rather a different something, could be born from our something, effectively resetting the cosmic stage abruptly. Finally, even in the heat-death scenario, some have mused about the possibility of random fluctuations creating new ordered patches. Given infinite time in a static de Sitter universe, the end state with dark energy domination, quantum fluctuations could occasionally, by sheer chance, produce a small region of lower entropy, perhaps even a new Big Bang seed, or a so-called Boltzmann brain, a spontaneously formed self-aware entity out of chaos. While these ideas are thought experiments and lead to some absurd-sounding consequences that physicists debate, often to argue that an eternal de Sitter phase might be problematic or that some new physics must intervene before infinity, they speak to the richness of considerations about eternity. Even in an endless nothingness, given unlimited time, perhaps a fluctuation might trigger a new creation event. The probability is incredibly low for any given moment, but in infinite time, the unlikely becomes inevitable. So perhaps heat death isn't truly the end. It could be a plateau before another beginning, in an endlessly cyclic multiverse of fluctuations. This is deeply speculative, verging on philosophical, but it shows that even finality might not be absolute. At this juncture, we've painted possible endings: eternal expansion into heat-death, a big rip, a big crunch with possible bounce, or a transition to something entirely different. Each path carries different implications for the arrow of time and for the question of whether the universe has a purpose or just a lifespan like any other natural phenomenon. From what we can tell now, with our cosmological measurements, the most likely fate is an ever-accelerating expansion leading to a very cold, very empty universe. Heat, death. But our knowledge is incomplete. Dark energy could surprise us by changing behavior. New physics, like interactions between dark energy and matter, or a slow dilution of dark energy, could alter the story. Now, let's step beyond even these questions of our universe's fate and ask, is our universe the only universe? For much of our narrative, we presumed that the universe meant all that exists. But modern physics has opened the door to the idea of a multiverse, a larger reality in which our universe is just one part. There are actually different notions of multiverse that scientists discuss. One arises from quantum theory, the many worlds. Interpretation suggests that all possible outcomes of quantum events actually occur, each in its own separate branch of reality. In that view, reality continually splits into a vast ensemble of parallel timelines. That's a kind of multiverse, a branching tree of universes coexisting in superspace. It's a very different concept from universes separated by space. It's more like parallel dimensions or alternate histories. It might not affect our cosmic story directly, so let's set that aside after noting it as an intriguing possibility. Parallel universes where, say, different events happened in history, etc., playing out side by side unbeknownst to each other. The multiverse idea, more relevant to cosmology, arises from cosmic inflation and string theory. If inflation occurred as our theories suggest, the ultra-fast expansion in the universe's infancy might not have been a one-time event that ended everywhere at once. There are strong reasons to suspect inflation is eternal. While it ended in our region, allowing our Big Bang fireball to proceed, in other far-flung regions, inflation might still be going on, endlessly creating more bubble universes. Picture a vast, inflating space-time, a kind of ever-growing foam. Occasionally, in that foam, regions stop inflating and crystallize into hot Big Bang bubbles like ours. Each bubble is a universe in its own right, with potentially different properties depending on slight quantum variations when inflation ended there. Our observable universe would be just one bubble that happened to nucleate 13.8 billion years ago. There could be countless others. These other universes are not located in our space. They are separated by continuing inflating space, which expands so fast that we can never catch up to the neighboring bubbles. They are forever out of reach. Each bubble might have different physical constants, particle content, even dimensionality, especially when combined with ideas from string theory. String theory suggests that the vacuum of the universe, the configuration of extra dimensions and fields, could have many possible states, sometimes quoted as 10 to 500 or more possibilities in the landscape of string theory solutions. Each bubble universe could realize one of those many possibilities. That offers a tempting explanation for why our universe has the peculiar laws it does. If there is a multiverse of all kinds of universes, we just happen to be in one that had the right conditions for galaxies, stars, and life, because otherwise we wouldn't be here to observe it. This is a kind of anthropic selection from a multiverse ensemble. It's important to note, none of this multiverse speculation is confirmed, but it is grounded in serious physics theories. Eternal inflation is a rigorous outcome of many inflation models. Once inflation starts, it generically doesn't stop everywhere, so while one bubble forms, inflation continues elsewhere, leading to potentially infinitely many bubble universes. And in string theory, the many possible shapes of extra dimensions, each giving rise to different physical constants, combined with inflation, virtually guarantees a multiverse. The inflating space fills itself with regions realizing all those options. Can we detect or observe evidence of other universes? It's challenging by definition. If they are truly separate, we can't see into them. But one possible sign would be if a neighboring bubble universe in the early inflationary period happened to collide with our bubble. That collision might leave an imprint, perhaps a circular pattern or a particular kind of distortion in the cosmic microwave background. People have actually searched CMB maps for hints of such collisions. So far, none have been convincingly found, but the search exemplifies how we don't shy away from trying to test even outrageous-sounding ideas. Another hint could come from the distribution of gravitational waves or subtle effects on the distribution of galaxies, none detected yet in a way that screams other universe. Another multiverse notion comes from higher dimensions and brane world scenarios. String theory requires extra spatial dimensions, 6 or 7 beyond our usual 3. Those dimensions could be compactified, curled up small, or in some models, we could be confined to a 3D brane floating in a higher dimensional space. There could be other branes, essentially other universes, separated from ours in the extra dimensions. Normally, we'd have no interaction with them except perhaps gravity, which can propagate in the higher dimensional bulk. Some have even imagined that a collision between branes could be what the Big Bang was. 2 3D worlds collided, releasing energy that flooded our brain with the hot matter of a Big Bang. If those other branes, universes, exist, they are right next door, in a sense, perhaps only a tiny distance away in a 4th spatial dimension. But we can't see them or touch them because our particles and light are confined to our own brain. It's a mind-bending concept. Other entire universes, potentially a millimeter away from us, in a direction we can't perceive. Whether it's bubble universes, parallel quantum worlds, or higher dimensional brane worlds, the multiverse idea profoundly changes the context of our cosmic story. Our universe could be a small chapter in an infinitely larger ensemble. It could mean that what we consider the ultimate beginning, the Big Bang, is just one local event in an eternally evolving multiverse. And it forces interesting questions. If there are countless universes, each with possibly different physics, what does that say about meaning? One could imagine each universe as having its own narrative, its own potential for life, or even intelligence. Are there other conscious beings out there, not just in our universe, perhaps in distant galaxies, but in entirely separate universes, forever causally disconnected from us? This drifts from science into philosophical wonder, because by construction, we may never verify those other universes. Yet, the theories that predict them, inflation, quantum mechanics, string theory, are in principle testable in other ways and have earned credibility. So we take the multiverse seriously, while acknowledging it currently lies at the speculative frontier. Regardless of whether there's a multiverse, we find ourselves in this universe, with its particular story. From a singular beginning, or at least an extremely hot, dense early state, our universe expanded, cooled, formed structures, and eventually produced us, beings capable of reflecting on the whole process. We've gone from contemplating mythic cosmologies to actually measuring the geometry and expansion history of the cosmos. We discovered the universe had a beginning, Big Bang, that it is 13.8 billion years old, that it expands, that it has a cosmic web of structure, and that it is dominated by dark matter and dark energy. These are incredible revelations, won through the hard work of observation and theory, building on generations of curious minds. Now we turn to the philosophical and existential implications of the cosmic story. Standing under the night sky, we can feel 2 seemingly opposite emotions: insignificance and profound connection. On one hand, the universe is vast beyond imagination. The Earth is a tiny pebble in a gigantic space. Even our galaxy, with 100 billion stars,
is just one in a sea of billions of galaxies. Physically, we occupy no privileged position. The cosmos is not arrayed with humanity at the center. We are off in a corner of an average galaxy, which itself is in a supercluster that is unexceptional among others. Time-wise, human history is an eye blink compared to cosmic time. The stars shone for billions of years before we came along. They will continue billions of years after we are gone. It's humbling, even daunting, to recognize this. The famous pale blue dot photograph taken by Voyager 1 from beyond Pluto, showing Earth as a tiny bluish speck in the void, encapsulates that humility. All of human history, every joy and sorrow, every hero and villain, played out on that mote of dust, suspended in a sunbeam in the vast darkness. When confronted with such scale, it's natural to feel small. Yet, on the other hand, how marvelous that we can comprehend this scale. We are made of particles that were forged in stars. Essentially, the universe gave birth to conscious organisms that can observe and contemplate the universe. We are a way for the cosmos to know itself, a sentiment popularized by Carl Sagan and profoundly true. Our atoms originated in the Big Bang, hydrogen, or in stellar furnaces, carbon, oxygen, nitrogen, etc., or in supernovae, iron, zinc, iodine, gold, all the heavier elements. We are literally children of the stars, made of stardust. Through us, the materials of the universe have become aware and curious. That imbues us, and possibly other intelligent life out there, if it exists, with a kind of cosmic significance, albeit a self-bestowed one. We carry the legacy of 13.8 billion years of cosmic evolution in our bodies. When we gaze out at the galaxies, those galaxies are in a sense observing themselves through our eyes. The emptiness of space, while vast, is not completely empty. It's filled with fields and particles and possibilities. Likewise, the perceived emptiness or pointlessness one might feel when confronted with a giant, cold universe can be filled with our own meaning and purpose. The cosmos doesn't hand us a script. Instead, it gives us the stage, the raw materials, and the invitation to create meaning. And humans have been doing that for as long as we have existed, through story, science, art, love, and exploration. We find that the more we learn about the universe, the more beautiful it becomes. Consider the fact that the atoms in your body were once inside of a star, perhaps many different stars over the eons. In a very real sense, you are as old as the universe, because the matter that composes you has been around since the beginning, apart from some recent transmutations via nuclear reactions. We are deeply connected to the cosmos. Every breath you take contains atoms from all over Earth and beyond, even some noble gas atoms that were forged in the Big Bang. The water you drink contains hydrogen made at the dawn of time. The calcium in your bones was fused in some star that ended its life long before Earth formed. We are a microcosm of the universe. This perspective can evoke a sense of spiritual awe, even in a non-religious framework. It's the awe of existence itself, the recognition that we are part of something vast and magnificent. The American astronomer Harlow Shapley said, "We are akin to the totality of things. The atoms don't belong to us, we belong to them. We are a moment in their journey." The universe's story also imparts lessons. One is the transient nature of all things. Stars are born and die. Even galaxies collide and merge. The universe evolves. Change is the rule. On Earth, we see that civilizations rise and fall, species come and go, all part of that cosmic change. But amidst change, there is continuity. The continuity of matter and energy, and the continuity of information passed on. Our sun inherited matter from previous stars. We inherited molecules from Earth's past life. We pass our atoms back to the Earth when we die. It's a kind of immortality, not personal immortality, but the persistence of our substance and our influence. A star that died billions of years ago in our region of the galaxy, by dying, It seeded the cloud that formed our solar system. In a way, that star lives on through us. Likewise, the choices we make and the knowledge we gain might propagate far into the future, indirectly shaping things we will never see. When we build a telescope and discover something, that knowledge changes the consciousness of humanity, which may alter our future actions and fate. Our cosmic understanding has also, interestingly, circled back to some ancient wisdom. Many cultures intuited a connectedness of all things, or a cycle of creation. The scientific specifics we've learned differ from the myths. The universe isn't literally the egg of a giant bird, for instance, but the emotional thrust that we are part of a greater whole is affirmed more strongly than ever by science. We now see that the same physical laws apply everywhere. We've sent probes to other planets and found familiar chemical processes at work. We've detected light from atoms in distant galaxies and found the same spectral lines as atoms we study in labs. The universe has a unity, and the story of cosmic evolution is a single, continuous narrative from the Big Bang to the present and onward to possible futures. We are a chapter in that narrative. In contemplating the end scenarios like heat death or Big Rip, one can feel despair. Will it all amount to nothing? But one might also find liberation in it. The distant future is beyond our control. What matters is what we do with the time and universe we have. The fact that the universe will end in one way or another does not negate the preciousness of its present. In fact, it enhances it. Just as mortal beings find meaning in life partly because it is finite, the finite window of a lively universe can galvanize us to appreciate its wonders all the more. We live in a cosmic springtime, when conditions are just right for complexity and life. It will not always be so, but how fortunate that it is so now, and that we are here to witness it. There's also a school of thought that even if our universe fades, perhaps life, or an advanced form of intelligence, could in some way continue or influence beyond its own universe. Some speculative ideas suggest extremely advanced beings might even hop between universes or create baby universes artificially. These ideas blur science and philosophy and remain in the realm of imagination for now. But the mere consideration expands our sense of possibility. Perhaps the end of the universe isn't an absolute wall, but just another frontier to transcend for a sufficiently ingenious civilization. It sounds like science fiction, and it certainly is right now, but who can definitively say what a Type 3 or Type 4 civilization, if it could exist, might achieve after millions or billions of years of evolution? Bringing our thoughts back to the here and now, the night sky. It connects us to all of this grand history and future. When you next stand under the stars on a clear night, think about the journey of a photon that enters your eye. Perhaps it left a distant galaxy when that galaxy was young and our planet not yet formed, traveling across expanding space for tens of millions of years, through voids and past clusters, until finally, one night it ended its journey on your retina, triggering a chemical reaction that led to an image in your brain. In that moment, you, a being of stardust, assembled on an 8-planet minor system around an unremarkable star, catch a whisper from the other side of the universe. And with collective effort, humanity has learned to interpret these whispers, to tell a coherent story of how we came to be. The cosmos is mysterious and beautiful. Every discovery seems to open new questions. We determined the age and shape of the universe, only to find most of its content is invisible, dark matter and dark energy. We may solve dark matter, perhaps a type of particle, and dark energy might remain puzzling or turn out to be a property of space itself. We look for potentially habitable exoplanets, wondering if life arose elsewhere. We tune our radios for possible signals from other civilizations, not knowing if we are alone or one of many. We delve into the quantum foam, attempting to reconcile general relativity, our theory of the very large, with quantum mechanics, the theory of the very small, hoping for a deeper understanding that might unify forces or reveal why the Big Bang happened the way it did. The quest goes on. Through it all, there is a human element that persists: wonder. As the astronomer Maria Mitchell said, "We reach forth and strain every nerve, but we seize only a bit of the curtain that hides the infinite from us." Yet, that bit of curtain has revealed an awful lot, and we continue to gently pull at it. Will we ever see the infinite, or the true beginning, or the full scope of the multiverse? Perhaps not, but the pursuit is part of what makes us human. The same impulse that made our ancestors paint constellations on cave walls and craft stories of creation now drives rockets and equations toward the heavens. Ultimately, the story of the cosmos is meaningful to us because it is also our story. We are not mere spectators. We emerged from this grand process. The hydrogen in our bodies, in every molecule of water, for instance, comes straight from the Big Bang. That means a part of us is as old as time. The carbon in our cells was forged in stellar hearts, making us the heirs of those stars. When we die, our atoms will return to the Earth, and eventually some will drift out to space again, maybe to become part of a new star or planet eons hence. In that sense, we are immortal, though our forms are temporary. So, what does it mean to be born from nothing? It means that existence is a gift against all odds, a tiny realm of something in an infinite sea of nothing. It means that perhaps nothing is unstable or pregnant with potential, that even a void can give rise to worlds. It suggests that reality is not a static block, but a dynamic story. Our universe began in a state devoid of structure, grew into a vast living tapestry, and will either continue to expand and evolve in complexity for some time, or eventually simplify again into quiescence. We got to observe a rich segment of that timeline, full of galaxies and life. That realization can fill one with a sense of reverence, not in a religious sense, but a profound respect for the majesty of nature. As our journey through the cosmos comes to an end, let's reflect on where we are. A small planet orbiting a medium star, on the edge of a galaxy that has at least 100 billion siblings, in a universe of maybe 2 trillion galaxies within our view, each brimming with stars and possibilities, all governed by the same physical laws, all born together in the same primordial explosion, all fated to either drift apart forever or perhaps crash together in some finale. We, ephemeral yet remarkable, stand here and through ingenuity have uncovered this story. It is a continuous, cinematic, emotionally resonant story, one that stretches from the beginning of time to the very ends of imagination. It's a story told by starlight and cosmic background whispers, written in equations and in the awe of anyone who looks up at the midnight sky. It's the story of the cosmos, our story. And though this particular telling of it must now conclude, the story itself goes on, written in the galaxies overhead and the atoms within us. As long as there are thinking beings to wonder and explore, the narrative will be retold, refined and cherished anew. In that sense, the cosmic story truly has no end. It lives so long as curiosity lives. So take a moment to step outside on a clear night. Feel the cool air. Look up. The light hitting your eyes has traversed the universe to reach you. The atoms in your body resonate with the history of the cosmos. The void may be vast, but you carry within you a universe of understanding that fills it with meaning. In the silence of the night, you can hear, if you listen closely, the echoes of the Big Bang and the songs of ancient starlight. The story of everything is speaking, and through our minds and hearts, the cosmos is listening to its own tale. In that communion, between the cosmos and our consciousness, lies a profound truth, that we are not apart from the universe. We are the universe, in small but significant part, and its fate and our fate are intertwined. From nothing we came, Into nothing, or something beyond, we may go. But in between, we have the chance to witness and marvel at the grandest of spectacles, existence itself. Let us be grateful for that chance. Let us keep the cosmic perspective, allowing it to illuminate our lives with both humility and wonder. And let us continue the journey, always, for as far as mind and imagination can reach, embracing the mystery and majesty of the cosmos. The cosmic saga continues, and we are fortunate narrators within it. The final line is not yet written, the quiet death of a sun-like star. It begins with a single light in the darkness. A star, solitary and brilliant, burns in the void. For ages untold, it has been a beacon, a steady, shining pinprick against the infinite night. Its light has traveled across the cosmos, a silent tale of its life. But now, something changes. The star's shine falters, ever so slightly. Its once unwavering glow begins to dim and flicker like a candle reaching the end of its wick. In this moment, we witness the opening lines of a final act, the beginning of a star's dying. Even the stars are mortal. For ancient peoples gazing up, the very idea of a star dying would have seemed impossible. The stars were regarded as eternal campfires of the gods, or the fixed points of the firmament. If ever a new star appeared, or an old one disappeared, as happened with rare supernovae recorded in history, they were seen as divine omens, not natural events. Only in modern times have we come to understand that these dramatic changes are the logical, even inevitable progression of a star's life. A star's birth, life, and death are part of the cosmos's story, not the caprice of deities. The star swells imperceptibly at first, then noticeably. Once contained and stable, it now grows bloated and luminous, turning a deeper shade of amber, then red. Its outer layers, no longer tightly bound, drift outward into space. If there were eyes watching from a nearby world, the star's transformation would paint the sky in hues of scarlet twilight, even at midnight. This ancient sun is becoming a red giant, a star near death, casting off the vestiges of its youth. Imagine standing on that distant world. The star that once gently rose and set now looms huge and ominous, filling a quarter of the sky. The air heats, and the ground cracks under a perpetual red dusk. Oceans, if they exist, begin to boil away as the star's dying light intensifies. The planet's sky is on fire. Day and night, a sullen ruby glow suffuses the heavens. For even when the star is below the horizon, its scattered light paints the atmosphere blood red. Any moons or nearby planets that once circled safely now face an inferno. The star's swollen photosphere might even reach out and consume its innermost planets entirely, erasing them in a final act of cosmic devouring. The once life-giving star has become a cosmic furnace, heralding doom. It is a breathtaking and terrifying spectacle, beautiful in its grandeur and heartbreaking in its finality. Why must even stars die? To answer this, we look into the heart of the star. For eons, in the core of that star, a mighty engine has burned. The star's purpose throughout its long life was to fuse the lightest elements into heavier ones, to take the simplest gas of the universe and forge it into something new. In its core, hydrogen atoms were pressed and squeezed so tightly that they merged into helium, releasing a tremendous burst of energy that made the star shine. This fusion is the star's heartbeat, a constant thrum pushing outward against gravity's incessant pull inward. Every second, countless atoms join together, and with each union, a packet of energy is born and fights its way from the core to the surface, eventually escaping into space as starlight. It is as if the star stands in a delicate balance, a perpetual tug of war, gravity drawing it inward, energy from fusion pushing outward. For a time that seems infinite to us, this cosmic heart pumps steadily, and the star remains in glorious equilibrium. neither collapsing under its own weight nor dissipating into the void. As long as the fusion fire burns in its core, the star lives on, an incandescent beacon of stability. But nothing in the universe is truly eternal. The star's fuel is finite, and one quiet day in the deep future, the fusion fire begins to falter. The hydrogen that sustained it for so long becomes scarce in the core. Like a lamp running out of oil, the light begins to change. With less outward push from the diminishing core fire, gravity tightens its grip. The core, no longer able to support the weight of the star's layers, starts to shrink. And as it contracts, something remarkable happens. It grows hotter, far hotter than it ever was during its placid youth. In that rising heat, a new kind of fire is kindled. The helium ashes, left from millions of years of hydrogen burning, suddenly become fuel themselves. In a furious flash, 3 helium nuclei slam together to fuse into carbon. The star's heart, which was faltering, gets a new surge of energy. It's like a second wind in old age, sudden, fierce, but short-lived. The core's collapse is halted by this burst of helium fusion. Bolstered from within, the star swells dramatically and becomes a red giant. Now our once small star is a swollen titan. Its outer layers have expanded hundreds of times over, cooling and glowing a rich, coppery red. To any distant observer, this aging star has become an enormous beacon, far larger and more luminous than it was in its youth. Yet its brilliance is deceiving. It is the brilliance of old age, not of vitality. Inside, the star is dying. The helium fuel at its core will not last long. Compared to the billions of years of its hydrogen-burning prime, the helium burns in a relative instant, in only a few % of that time. The star is living on borrowed time, using up its last reserves in a final prodigious blaze. In the star's final breaths, it becomes unstable. It pulsates, expanding and contracting, as if it were a gigantic cosmic lung drawing ragged breaths. Each expansion and contraction is vast and slow, taking perhaps years or decades, but in the life of a star, it is a frantic oscillation. With each pulse, the star sheds some of its outer gas into space, like a series of sighs, creating shells of material that drift away into the surrounding darkness. Between pulses, the star's hot core shines through more clearly, its intense radiation pushing on the remaining layers. A stellar wind, a stream of particles from the star's surface, begins to blow the star's atmosphere outward. The dying star is both lamenting and creating with these breaths, for the gas it expels is rich with elements forged over its lifetime. Carbon formed in the star's core now flows outward in gentle currents. The star is painting its own epitaph in the skies around it, layer by layer. At last, the star can no longer hold onto its outer layers at all. One final large pulse or wind sweeps them completely into space. The great bloated red giant effectively sloughs off its entire outer envelope. All that remains behind is the hot, naked core of the star, now exposed to the cosmic vacuum. For a brief moment in cosmic time, that core, small as it may be, perhaps only the size of Earth or smaller, shines fiercely. It is incredibly hot, having been the furnace at the star's center, and now with no overlying layers to obscure it, it radiates intense ultraviolet light into the space around it. The formerly expelled outer layers, drifting nearby, suddenly find themselves bathed in this energetic glow. They begin to fluoresce, lit up from within like a neon sign. A shell of multicolored gas materializes around the star's core, expanding outward. This is a planetary nebula, the quiet, haunting aftermath of a star's gentle death. Under the gaze of telescopes, it appears as a delicate bubble or ring of glowing gas, expanding gradually into interstellar space. To an eye peering from afar, it might resemble a ghostly flower blooming in the dark garden of the galaxy, a final blossom from the star that was. The colors of this nebula can be vivid, subtle greens and blues from oxygen atoms, reds from hydrogen, all mixing into an ethereal pastel tapestry. The shapes are surprisingly intricate. Some nebulae form perfect spheres or rings, while others are sculpted into hourglass forms or butterfly-like wings by the star's magnetic fields, or perhaps by the gravity of unseen companion stars. At the center of this luminous cloud floats the small stellar core, now called a white dwarf. It is a stellar corpse, extremely hot but fading, shining only with leftover thermal energy. A white dwarf is usually no larger than a planet, yet contains nearly the mass of the original star. It's incredibly dense. The star's mass is now crushed into a sphere perhaps the size of Earth. The matter inside is in a strange, degenerate state. Atoms pressed so close that electrons are squeezed free of their orbits. No fusion fires burn in this core anymore. It glows like an ember taken from a fire, brilliant at first, but destined to dim over the eons as it cools. Such is the quiet death of an ordinary star. A star like this one, perhaps like our own sun someday, does not end in violence, but in a peaceful casting off, a cosmic setting of the stage. Its final act is to illuminate the gases of its own shed self, creating a hauntingly beautiful nebula that will linger for only a few millennia before dispersing into the surroundings. That glowing shell is a brief memorial, a glowing epitaph written in space, commemorating the star's existence. In time, even that nebula will fade, its atoms drifting away to mix with the interstellar medium. In dying, the star returns its substance to the galaxy. The elements it formed, carbon and nitrogen from its later fusion, and even new molecules forged in the cooling breath of its final winds, are cast back into the cosmic reservoir. The star's death is an ending, but also a bequeathing. Its carbon will become the seed of new organic molecules. Its dust may gather into future planets. In this gentle goodbye, the star enriches the universe with the products of a lifetime. Yet not every white dwarf rests quietly forever. If a small star's corpse orbits in a close binary system with another star, it may later find a way to die a second, more violent death. As a white dwarf steals gas from its companion, it grows heavier until reaching a critical weight. At that point, its carbon heart can ignite in one furious wave of fusion, consuming the star from within. In a matter of seconds, the white dwarf is blown to bits, a titanic thermonuclear explosion. This is a type of supernova as well, often called type Ia by astronomers, and it can rival the brightness of a core collapse supernova. In this scenario, the entire star is destroyed, with no neutron star left behind, just an expanding cloud of debris rich in newly forged elements like iron and nickel. Even a star that lived quietly can thus end in sudden violence if given this final push. Such explosions are another way the galaxy is seeded with the heavy elements that will become part of new cosmic generations. The explosive death of massive stars. Now, consider a star far more massive, a true stellar giant many times heavier than our Sun. Such a star, born with tens of times the Sun's mass, lives a very different life and meets a far more dramatic end. Where a smaller star like the Sun quietly sloughs off its outer layers, a massive star lives and dies in raging fire. It is a brilliant blue-white beacon during its life, far hotter and more luminous than an average star. It burns its fuel at a prodigious rate, living fast and dying young, as one might say. For millions of years, a mere blink compared to the billions our Sun will enjoy. This massive star fuses the lightest elements in its core at a feverish pace. Its core temperatures and pressures soar much higher than those in smaller stars, and the chain of nuclear fusion proceeds beyond just hydrogen to helium. Once helium is exhausted, the core, under crushing gravity, contracts and heats again, and new fusion reactions ignite in succession. Carbon burns into neon, neon to oxygen, oxygen to silicon, step by step forging heavier and heavier nuclei. Each new fuel is consumed faster than the last, as if the star knows its time is short and rushes through one element after another. Deep in the heart of this giant, a ball of iron begins to form, and with it, the star's fate is sealed. Iron is a strange endpoint for the star's nuclear alchemy. Unlike the lighter elements, fusing iron does not release energy. Instead, it greedily absorbs energy. All the star's prior steps of fusion had been exothermic, releasing the energy that held the star up. But when enough iron accumulates in the core, further fusion becomes futile. The stellar engine that has thrummed for millions of years suddenly sputters and stalls as it tries to fuse iron. In a star so huge, this failure is catastrophic. Gravity, which has been held at bay for so long by the outward pressure of fusion, now has no effective counterforce in the core. There comes an instant, a final unforgiving moment, when the iron core can no longer support the enormous weight of the star's outer layers. In the blink of an eye, the core collapses. A star that dwarfs our sun in size implodes in less than a second. The iron atoms in the core, under the extreme pressure, are crushed together. Protons and electrons merge into neutrons in a burst of particle transformations. The core, which might have been the size of Earth, shrinks to a sphere only a few tens of kilometers across and is as dense as an atomic nucleus. The collapse releases an almost unimaginable amount of gravitational energy, heating the core to billions of degrees. A flood of neutrinos, nearly massless ghostly particles born of nuclear reactions, erupts from the core and flies outward. In fact, so much energy is carried by these neutrinos that for a brief moment, they outshine the star's luminous output by a factor of hundreds. It is as if the star's soul is escaping in the form of these ghost particles, rushing out in all directions. This is the opening of the most violent event in the star's life. The core collapse triggers a supernova explosion. The infalling outer layers of the star, which were rushing inward following the collapsing core, slam into the now rock-hard wall of densely packed neutrons that the core has become. In that violent collision, the infalling matter rebounds. A powerful shockwave forms and begins to propagate outward. The shock, energized by the deluge of neutrinos streaming from the core, plows through the star's layers, tearing them apart. Within hours, the shock reaches the star's surface and blasts the star apart in one titanic explosion. The star that once shone steadily is now gone, and in its place is a swelling fireball of stellar debris. For a brief time, this single dying star outshines its entire galaxy. What was once a distant point of light now becomes a beacon so brilliant that it can be seen across millions of light years. If there were civilizations looking up from planets in that galaxy, they would see a searing new star light up the sky with ferocious intensity, perhaps casting shadows at night and outshining their moon. On Earth, even though such explosions are rare in our galaxy, humans have recorded a few over the centuries. Ancient skywatchers around the world noted guest stars suddenly appearing in the sky, bright enough to be seen in daylight for weeks. They were witnessing supernovae, though they did not know it, the death flashes of giant stars. In modern times, astronomers have captured many such events in other galaxies. In the late 20th century, they witnessed a supernova in a nearby dwarf galaxy, the brightest seen in almost 400 years. For weeks, it glared in the southern sky, a stark reminder that even the heavens can erupt without warning. A supernova pours out not just visible light, but every form of electromagnetic radiation, from searing X-rays and gamma rays to long, lazy radio waves. It also launches matter at incredible speeds, a hurricane of gas and dust racing outward. The energy of a supernova defies easy comprehension. In those few seconds of collapse and rebound, the star releases more energy than it did in its entire millions of years of normal life. People sometimes say it's like a billion suns lighting up at once. If a supernova were to occur within a few dozen light years of Earth, it could outshine our moon and potentially disrupt the biosphere with its high-energy radiation. Yet, from a safer distance, it would be one of the most glorious sights in the universe. A cosmic firestorm, the sudden blossoming and slow fading of a star's last light. And amidst this destruction, there is creation. In the heart of the supernova explosion, the chaos and heat forge new atomic nuclei that the star never could while it lived. The shockwave's extreme conditions allow atoms to slam together and capture neutrons rapidly. Elements heavier than iron, which the star could not produce in its normal life, are manufactured in these brief moments of fury. Gold, silver, platinum, iodine, uranium. The universe's precious metals and rare elements are born in the crucible of the exploding star. Before stars, the universe held only the lightest elements: hydrogen, helium, and a dash of lithium from the Big Bang. All the rest, carbon and oxygen, iron and gold and beyond, were forged in stellar furnaces and in these titanic explosions. In this way, almost every element heavier than helium is a gift from stellar lives and deaths. Atomic nuclei absorb neutrons in rapid succession. Later, those neutrons decay into protons, transmuting the elements into heavier ones on the periodic table. The star, in dying, becomes an alchemist on a cosmic scale. The brilliant glow of the supernova begins to be tinged with the spectral signatures of these freshly minted elements. When the debris eventually cools enough, these atoms will combine into dust grains, floating through space, awaiting incorporation into future worlds. Thus, the star's violent death is also a moment of genesis, the birth of new materials that will enrich the galaxy. What remains after such a cataclysm? As the glare of the supernova fades over weeks and months, and the expanding cloud of ejected gas thins out, we peer into the aftermath to find a newborn object at the center. If the original star was massive but not too extreme, perhaps up to 20 times the sun's mass, the core that's left behind is a neutron star. This neutron star is a tiny, ultra-dense sphere, only about as wide as a city is long, yet containing more mass than the entire sun. It is essentially a giant atomic nucleus, a ball of neutrons packed shoulder to shoulder. In fact, the first supernova explosion observed by ancient sky watchers, a guest star in the 11th century, whose remnants form a beautiful nebula visible today, left behind a neutron star that still sits at the center of the expanding cloud, spinning and flashing. For a neutron star is not a quiet thing, at least not at first. Neutron stars, pulsars, and magnetars. Often, the newborn neutron star is incredibly hot and endowed with a rapid spin inherited from the core of the star that collapsed. Conservation of angular momentum, the same principle that makes an ice skater spin faster when they pull in their arms, means that a core that was spinning moderately will whirl madly as it shrinks. A neutron star can rotate dozens or hundreds of times each second. Along with this spin, it carries an immensely strong magnetic field, intensified by collapse, just as the spin was. The result is one of the universe's most astonishing phenomena: a pulsar. Bright hotspots form at the neutron star's magnetic poles, where intense beams of radiation shoot outward. As the neutron star rotates, these beams sweep around like the lighthouse beams on a dark shore. If Earth lies in the path of those beams, we see the neutron star blinking on and off regularly. A cosmic lighthouse marking the location of the lost star. When the first pulsar was discovered in the 1960s, its signal was so regular, a pulse every 1.3 seconds, that the astronomers half-jokingly named it LGM-1 for Little Green Men, thinking it might be an artificial beacon. Soon they found more, and realized these were not alien signals, but the heartbeats of dead stars. These neutron stars are among the strangest objects in existence. A teaspoon of neutron star material on Earth would outweigh a mountain. The gravity at its surface is so immense that if you dropped a marshmallow from a few feet above, it would hit the surface with the energy of a nuclear bomb. The neutron star's magnetic field is trillions of times stronger than Earth's. In some neutron stars, called magnetars, the field is so ferocious that it can distort the very structure of atoms and unleash bursts of high-energy radiation. Magnetars occasionally experience starquakes as their rigid crusts crack under magnetic stress, releasing tremendous flares of gamma rays. In 2004, a magnetar on the other side of our galaxy erupted, and even from tens of thousands of light years away, it briefly ionized Earth's upper atmosphere. These exotic stellar remnants may be small, but they can be more energetic in certain moments than almost anything else in the cosmos. The neutron star gradually cools and slows its spin over many millennia, especially if it has no companion feeding it fresh energy. Its lighthouse beams dim. In the far future, that neutron star may become practically invisible, a cold, dark sphere of neutron matter drifting silently through the galaxy like a spent coal from a great fire. But at least initially, in the aftermath of the supernova, it is very much an active presence, a cinder with a fiery glow. In some supernova remnants, the neutron star's wind of high-energy particles continues to energize the ejected gas long after the explosion, making the nebula glow in fantastical shapes and colors. If the original star was even more massive, say on the order of 20, 30 or more times the mass of our Sun, then even the neutron star outcome is denied. In these cases, the core that tries to form a neutron star might be so heavy, more than a few times the Sun's mass, that not even the degenerate pressure of neutrons can hold it up against gravity. Nothing in nature can withstand the gravitational crush of such a massive core. Black holes, the ultimate collapse. In that case, the core collapses further, past even the neutron star stage, and vanishes from view entirely. The star's core becomes a black hole, an object so dense and with gravity so strong that within a certain boundary, not even light can escape its pull. Around this collapsed point lies the event horizon, the spherical surface marking the point of no return. Space and time themselves are warped around this region. If we could watch the dying massive star's final moment of collapse to a black hole from a safe distance, we would never actually see it disappear. Instead, we'd see the star's image freeze and dim as the last light it emits gets stretched to redder and redder wavelengths, time appearing to almost stop at the brink of the event horizon. In reality, the star's core continues to collapse beyond our view, but the information about it is forever hidden behind that horizon. The newly formed black hole now contains the mass of several suns in a sphere only a few kilometers wide. Its gravity is a pit from which nothing escapes. A black hole is the most extreme remnant of a star. The core of the star has been compressed beyond any known limit. At the center lies a singularity, a point of almost infinite density, shrouded by the event horizon. But contrary to popular myth, a black hole is not a cosmic vacuum cleaner indiscriminately devouring everything in sight. If our Sun could be instantly replaced with a black hole of the same mass, Earth's orbit would remain unchanged, though our world would freeze without sunlight. One has to get very close to a black hole, inside the Schwarzschild radius, to be irretrievably pulled in. Sometimes, the demise of a very massive star can create an even more spectacular signal. If the star was rapidly spinning and had strong magnetic fields, the collapse into a black hole can produce jets of material shooting outward from the poles at nearly the speed of light. These jets drill through the collapsing star and burst out into space as intense beams of gamma rays. We call this event a long gamma ray burst. For a few seconds, A gamma-ray burst from a collapsing star can be the brightest electromagnetic event in the observable universe, detectable across billions of light-years. It's a dying star's last scream, a focused, deadly burst of energy indicating the birth of a black hole. Satellites have recorded many gamma-ray bursts, and in some cases have spotted the faint afterglow from the exploding star's remains, confirming that they were indeed massive stellar explosions, likely linked to black hole formation. In rare cases, a massive star might even collapse directly into a black hole with no supernova explosion to herald it. The star's core simply implodes and keeps imploding as the infalling outer layers follow it past the event horizon. From the outside, one might witness the star suddenly dimming and disappearing, as if a trap door opened beneath it. For a brief moment there could be a burst of neutrinos or a slight gamma-ray flash, but no brilliant supernova blast. Such an event is sometimes termed a failed supernova. In recent years, astronomers identified a candidate, a massive star in a nearby galaxy that brightened slightly, then faded away to nothing, leaving no trace. It seems that nature can be both extravagant and miserly with its farewells. Some stars go out in a blaze of glory, while others quietly wink out, leaving darkness and a newfound black hole where once a star shone. As many as a third of the most massive stars may die in this undramatic way, simply collapsing into the void. These are truly the most secretive of stellar deaths. Aftermath, ghosts and rebirth. Whether through a titanic supernova or a quiet collapse, the end of a massive star leaves space forever changed. The debris cast off from the explosion races outward at millions of kilometers per hour, a shockwave plowing into the surrounding interstellar gas. Over years and decades, observers with telescopes can see this shell of debris expanding, a ring of sorrow growing larger but fainter as it dissipates its energy into space. This glowing remnant, enriched with all those new heavy elements, mingles with the interstellar medium, the tenuous gas between stars. In time, that gas may become the raw material for new stars and planets. A supernova's remnants are like the scattered ashes from which new life will emerge, glittering, multicolored nebulae cooling into the darkness. Sometimes, amid those remnants, the core that was left behind makes its presence known. In one famous supernova remnant, a pulsar spins madly, lighting up the surrounding cloud with pulses of energy and winds of particles that cause the gas to glow. In other cases, if the remnant core was a black hole, we might see high-energy X-rays or gamma rays if the black hole is consuming material around it. Often, however, the black hole simply is, unseen, its gravitational field the only testament to a star that once shone. Now our journey takes an even stranger turn. The death of one star, spectacular as it is, can give rise to an even more dramatic event under the right circumstances. Consider a binary star system, two stars orbiting one another in a celestial dance. If both stars are massive enough, both might eventually become supernovae in their time, leaving behind two neutron stars orbiting their common center. Over millions of years, their gravitational dance continues, but with each orbit, they draw imperceptibly closer. Their spiraling movement generates gravitational waves, ripples in the very fabric of space-time, that carry energy away and bring the neutron stars ever nearer to collision. Kilonovae, cosmic collisions and gravitational waves. Finally, long after they were born, these two city-sized remnants meet their fate together. They collide and merge in a violent embrace. In that moment, a new kind of fire ignites. The merging of two neutron stars creates an event we call a kilonova, a cosmic flash that, while not as bright as a supernova, shines 1,000 times brighter than an ordinary nova. For a few days, the site of the merger glows with a blue then red light. It is an event both fierce and brief, a final fireworks display from the corpses of stars. The physics of this collision is extraordinary. When neutron stars merge, their incredibly dense matter gouges and shocks itself, forming exotic heavy elements in profusion. If supernovae are one forge for the heaviest elements, kilonovae are another, perhaps even more prolific for certain treasures. In the debris tossed out by the merging neutron stars, astronomers have detected signatures of gold and platinum being created in astonishing quantities. In mere seconds, more gold may be forged than in all the cores of stars over billions of years. The kilonova's glow is powered by the decay of these new, unstable heavy atoms as they release energy. Alongside the light of the kilonova, the merger rings the universe like a bell. Gravitational waves ripple outward from the collision, stretching and squeezing space-time itself. By the time these waves reach us, they are faint echoes, but with sensitive instruments, we have learned to listen for them. In recent history, humanity has detected such ripples, hearing the chirp of two neutron stars colliding in the depths of space. In tandem, telescopes caught the delicate afterglow of the kilonova, marking the first time we both saw and heard a cosmic event of this magnitude. In some neutron star collisions, the two merging stars might collapse into a black hole immediately after the merger, swallowing some of the heavy element-laden debris. In others, they might form an extremely massive neutron star that survives for a brief time. But either way, they leave a changed environment rich in freshly minted elements. These elements will drift through space, become part of gas clouds, and one day be incorporated into new worlds. It is awe-inspiring to realize that the gold in a ring on a person's finger likely came from such a merger of two long-dead stars, billions of years ago in our galaxy. The violence of that moment becomes the gentle gleam of metal we see and cherish, a direct connection between cosmic catastrophe and human ornament. Observing stellar death. Throughout all these scenarios, humanity has slowly learned to read the messages in the skies that reveal these processes. How do we know these tales of dying stars when no human has watched a single star go through its entire life cycle? The truth is, the universe has left clues for us, and with our ingenuity, we have learned to gather them across the light years. We piece together the story of stellar death from many different kinds of observations across many types of cosmic messengers. First and foremost, we see the light. Visible light from supernovae has been recorded by sky watchers for millennia. From the sudden appearance of guest stars noted in ancient chronicles to the careful telescopic monitoring of distant galaxies by modern astronomers who catch supernova flickering into brightness like cosmic fireflies. We have captured images of glowing planetary nebulae around dying sun-like stars, each a snapshot of a star's final sigh. We have seen the expanding shockwaves of supernova remnants, their tendrils growing over years in photographic time-lapse, confirming that they are indeed blasts in slow motion. But light is just one messenger. We have also learned to detect radio waves, which reveal phenomena invisible to our eyes. In the radio spectrum, pulsars announce themselves clearly. Their lighthouse beams become pulses of radio emission that our radio telescopes can pick up. The very discovery of neutron stars came from radio astronomy. To this day, radio observatories map the intricate structure of supernova remnants, picking up the radio glow of electrons spiraling in magnetic fields there. Through radio eyes, we have seen the remnants of star death stretching across vast swaths of sky, invisible in ordinary light. Then there are the neutrinos, those ghostly particles that rarely interact with matter. When a massive star's core collapses, an enormous number of neutrinos are released. In one famous supernova, underground detectors on Earth registered a sudden burst of neutrinos. a full few hours before the supernova's light became visible in the night sky. Those neutrinos had raced out from the collapsing core, heralding the death of the star before the light from the explosion could fight its way out. It was the first and only time so far that we directly detected such a neutrino burst, and it confirmed our theories about what happens inside a dying star's core. Now we wait eagerly for the next nearby supernova, knowing that neutrino detectors will ring like alarm bells, perhaps even allowing us to witness the core collapse in neutrino signals ahead of the light show. In recent years, we have opened our ears to the gravitational waves, adding a whole new sense to our astronomical repertoire. When massive objects like neutron stars or black holes collide, they send out ripples in space-time that travel across the universe. Detectors on Earth have picked up these tiny distortions as they pass by. Through gravitational waves, we heard the final moments of binary black holes merging, events completely dark to electromagnetic telescopes. We also heard, and then saw, a pair of neutron stars collide and light up a kilonova. Gravitational waves have allowed us to confirm directly that yes, black holes and neutron stars do merge exactly as long predicted, releasing energy not as a flash of light, but as a faint trembling of the cosmic fabric. It's as if we developed the sense of hearing after millennia of only seeing. Whole new phenomena have become perceptible. Each type of messenger, light, radio waves, neutrinos, gravitational waves, gives us a different insight into the death of stars. By combining them, an incredibly detailed and holistic picture emerges. For example, by studying a supernova's light alone, we learn about its energy and composition. By catching neutrinos from it, we peer directly into the core collapse physics. By listening for gravitational waves, we might witness the formation of the neutron star or black hole in real time. The universe has been gradually revealing its story through these multiple channels, and we have become adept at tuning in. Armed with this knowledge, we can turn our attention to the star that matters most to us, our Sun. The Sun is a fairly ordinary star, midway through its life, but one day it will undergo its own deathly transformation. It will not explode as a supernova. It lacks the mass for that ferocious end, but the Sun's demise will nonetheless be a dramatic and profound event, especially from the perspective of any living beings that might witness it. The fate of our Sun. In about 5 billion years, an unimaginable span to us, yet a fixed and finite countdown in cosmic terms, the Sun will exhaust the hydrogen fuel in its core. As it begins to run out of gas, the Sun's core will contract and heat up, and, just as we described for a smaller star's final stages, helium fusion will ignite. Our star will swell into a red giant. In those distant days, the Sun will expand to hundreds of times its current diameter. Mercury and Venus, the inner planets, will almost certainly be engulfed, devoured by the Sun's bloated fiery plasma. Earth's fate is less certain. Some calculations suggest it might just escape engulfment, spiraling outward a bit due to the Sun's mass loss. But even if it isn't swallowed whole, it will be scorched and sterilized. The oceans will boil off, the atmosphere will escape, the surface will become a molten hellscape. For any distant observer in those future times, our Sun's transformation will be a sight to behold. What was once a gentle yellow star will balloon into a red monster dominating our solar system. In the solar system's far future, perhaps an intelligent species, whether human descendants or some other beings, might watch the Sun's angry metamorphosis from a safe haven, maybe on the moons of Jupiter or Saturn. They would see the Sun, day by day, grow larger and redder, its brilliance tinged blood orange. The familiar constellations might fade in its overwhelming glare. The heat would rise even in the outer solar system. By then, Earth, if it still exists, would be a glowing ball of magma. Eventually, as the Sun reaches the apex of its giant phase, it will begin to pulsate and cast off its layers. It might produce a beautiful planetary nebula of its own. Our Sun which once lit the solar system with a crisp golden light, will create a vast bubble of fluorescent gas, expanding outward past the orbits of the inner planets. At the center of that nebula will shine a pinpoint of intense white light, the sun's core laid bare as a new white dwarf.
Imagine, for a moment, what that will look like from a vantage point at the edge of the solar system. Perhaps from the twilight skies of Pluto, or some dwarf planet far beyond Neptune, one might see the whole sky dominated by the glowing cloud of the sun's planetary nebula. It could appear as a huge, circular rainbow cloud, slowly fading over thousands of years. The white dwarf sun would be incredibly luminous in ultraviolet, causing the nebula to fluoresce. In time, the nebula would disperse, and all that would remain of our sun would be that white dwarf, a hot, Earth-sized ember composed mostly of carbon and oxygen, the products of helium fusion in the sun's final throes. It will shine bluish-white at first, equal in brightness to perhaps 1,000 present-day suns. But being so small, it will cool and fade over billions of years. Eventually, long after the planetary nebula dissolves and blends into the galactic background, the sun's remnant will become a black dwarf, effectively invisible. Our solar system will not be spared the universal law of change. The surviving planets, perhaps Mars, Jupiter, Saturn, and the outer worlds, will find themselves orbiting a tiny, dense star where once a bright sun shone. The night sky on those worlds will be dark, the familiar warmth and light of the sun replaced by a dim pinprick. Perhaps, in that far future, nothing of Earth remains but some drifting debris or baked rocks orbiting the white dwarf. Or maybe Earth's material will have been blown into the planetary nebula, its atoms mixing with the sun's, and eventually traveling outward. In that case, part of what was once our world will eventually become incorporated into new star-forming clouds elsewhere. It's a melancholy vision, the extinction of sunlight as we know it, the end of Earth as a living planet. Yet, viewed from a broader lens, it is also beautiful. The sun's death will contribute to the ongoing cycle of cosmic renewal. The elements from our sun and Earth will be redistributed. Perhaps, many billions of years hence, some of those atoms might find themselves in new star systems, potentially part of new life forms that will walk on new worlds and look up at their skies, never knowing that the atoms in their bodies once warmed a place called Earth under a star that died to make their own existence possible. The cycle of stellar life and death thus directly touches the cycle of life and death on planets. The end of starlight. Looking even further into the future, beyond the fate of individual stars like our sun, we confront the ultimate destiny of starlight itself. The universe is almost 14 billion years old now, and it is ablaze with stars. But it will not always be so. Trillions of years from now, the era of starlight will wane. The great spiral and elliptical galaxies we see today will have merged and transformed. Star formation, which requires dense clouds of gas, will slow and eventually cease as those clouds are used up or dispersed. The remaining stars will age and die without replenishment. The cosmos, now so full of glittering galaxies, will grow darker and quieter. The last stars to shine will be the low-mass red dwarfs. These tiny fires burn their fuel so slowly that none have died yet in the current age of the universe. A red dwarf with just a fraction of the sun's mass can fuse hydrogen not only in its core, but throughout its churning interior, eking out its fuel with extreme thrift. Some red dwarfs are expected to live for trillions of years. But even their time will come. Eventually, even the smallest stars will exhaust their hydrogen. Unlike the sun, a red dwarf may not become a red giant in a dramatic flourish. It lacks the mass to ignite a shell of helium in a grand expansion. Instead, when a red dwarf finally runs out of fuel, it will quietly contract and heat up, turning into a hotter blue dwarf stage, according to theory, then gradually cool and fade.
It may bypass the classic planetary nebula stage entirely, ending up as a helium white dwarf if it was very low mass, or a mostly inert ball of helium and other elements. In either case, its light will slowly dim to blackness. Because the universe is not yet old enough, we have never seen this final stage of a red dwarf, but we know it must happen. In that far future, galaxies will be populated mostly by stellar remnants, white dwarfs, neutron stars, black holes, and perhaps a few slowly cooling red and brown dwarfs. The fading of all stars will usher in the so-called degenerate era of the universe. Picture the cosmos at that time. Galaxies have gravitationally merged into enormous clusters or been flung apart by the accelerating expansion of the universe. The night sky of a planet, if planets still exist, orbiting a black dwarf might be nearly completely dark. No new stars twinkle, only the occasional flicker of a distant supernova from a galaxy still having a last gasp of star formation, or perhaps the weak glow of a sparse constellation of fading red dwarfs. Over exceedingly long times, even those faint lights will wink out. The universe will become a quieter place. Gravity will continue to sculpt the fates of these remnants. In galaxy cores, more black holes will merge and grow. Some stray white dwarfs or neutron stars might collide, producing one last supernova or kilonova here and there, a final cosmic fireworks to break the deepening night. For instance, two orbiting black dwarfs, the end states of most sun-like stars, might eventually inspiral and merge due to gravitational wave emission, creating a brief flare of energy or even igniting a strange supernova if they somehow fuse into a new massive object. Or, as speculative physics suggests, in an unimaginably distant future, quantum tunneling could cause heavy elements in an extremely cold white dwarf to undergo fusion, triggering a so-called black dwarf supernova. If this happens, these would be the last dazzling blasts of the universe, silent, forlorn sparks as the cosmos sinks into dormancy. As time stretches on, if our understanding of particle physics is correct, protons, the hearts of atoms, might be unstable over stupendously long timescales. If proton decay is real, then given enough time, even the matter comprising the dead stars will dissolve. The solid iron in a black dwarf, the neutrons in a neutron star, all could eventually decay into lighter particles, turning the remnant entirely into radiation and perhaps leptons, like electrons and positrons. If protons don't decay, then these remnants might persist essentially forever, but even then, they won't shine or significantly interact. They'd be eternal dark monuments. Black holes, the last truly gravitationally bound structures, also have their own endgame. Through Hawking radiation, a quantum mechanical process where black holes can slowly leak particles and energy, even black holes will eventually evaporate. A black hole the mass of the Sun would take an outrageous amount of time to evaporate, far longer than the current age of the universe. More massive ones would take even longer, practically enduring for eternity on human timescales. But given enough time, even these giants will eventually fizz away, each ending in a final weak burst of light as their last energy radiates into the void. After all of this, the universe will have reached a state often called heat death, or the Big Freeze. No organized sources of energy remain, just a thin soup of particles and photons gradually tending toward a uniform temperature as everything expands. The era of starlight will be a distant memory. The universe, born in fire and sustained for eons by the light of trillions upon trillions of stars, will pass into an age of darkness. It is a sobering picture, a cosmos without stars, without warmth, without structure beyond the quiet drift of elementary particles. One might wonder, what was the point of all these brilliant lives of stars if it all ends in such stillness? It forces us into existential contemplation. But within that grand arc, from bright beginning to quiet end, lies a profound truth. During the epochs when stars shone, so much happened. Stars lit up the galaxies, made possible the existence of planets and life, and gave the universe complexity and beauty. Their deaths, especially, were crucial. Without the dying of stars, the universe would be sterile. The heavy elements needed for rocky planets, for water, for the chemistry of life, none of those would exist without supernovae and kilonovae. Dying stars seeded the universe with diversity. We are made of stars. We ourselves are living proof of the productive value of stellar death. Every one of us is made of stardust. This phrase has been said so often that it risks sounding cliché, but it is profoundly, literally true. The carbon in our muscles and skin was created by a star of moderate mass in its red giant phase, gently blown into space before that star became a white dwarf. The iron in our blood was forged in the core of a massive star and dispersed in a supernova explosion. The calcium in our bones, the oxygen we breathe, the phosphorus in our DNA, all were synthesized in stellar furnaces and spread through stellar farewells. Even elements like gold that adorn our rings or electronics were fashioned in the extreme environment of merging neutron stars. We are, in a very direct sense, the ash of stars, molded into conscious beings who can contemplate the cosmos. The deaths of stars made our lives possible. Their endings were our beginnings. Think about it. The gold in a wedding ring was flung into space by the merger of neutron stars in some ancient cataclysm before the Earth existed. The nitrogen in the DNA of every living cell was created in an aging star's envelope and gently blown into space by a stellar breeze as it died. The iron that binds oxygen in your blood was minted in the core of a massive star and scattered across the galaxy by a supernova's shockwave. Each of us carries the story of star death in our bodies. When we gaze at the night sky, we are looking at the past, not just the light from distant stars, but echoes of events that made our own existence possible. In this way, the death of stars is not merely an end, but a transformation. In their destruction, stars sow the seeds of creation. From the wreckage of a supernova, new solar systems will one day form. In the glowing planetary nebula of a gentle star's passing, the gas will mix and mingle into the galactic clouds that spawn new generations of stars. Stellar death rejuvenates the cosmos, keeping it enriched and diverse in composition. There is an existential poetry in this cycle. The stars do not live forever, and neither will the universe as we know it. But in their fleeting lives, they build the complexity that allows future wonders to emerge. They sacrifice themselves to give light and elements to the next generation. Without the death of countless stars before our sun was born, our planet could not have rocks or water or life. We owe our existence to 1 billion stellar funerals. As we close this journey, imagine once more that single star fading from the sky. Its light, which may have shone on ancient oceans of some far-off world, now dims. To any living creatures depending on it, this would be a catastrophe beyond comprehension, a slow apocalypse. And yet, in the cold and dark aftermath, the materials shed by that star will drift and eventually coalesce into new forms. Perhaps a new star, smaller and steadier, will one day form from that very material, and around it new planets. What was once a day's end for one world might become the dawn for another. The universe is a grand tapestry of beginnings and endings, and the death of stars is one of its most stirring threads. It reminds us of the impermanence of even the mightiest engines of creation and the interconnectedness of all things. Through stellar death, the cosmos teaches a simple lesson. From endings come new beginnings. Each flicker and flash, each quiet extinguishing, leaves something behind for those who follow. In our minds, let us wander under a sky full of stars, knowing that above us are not just points of light, but stories. Each star is a story of a life that will someday end. of an element factory that will one day shut down, of a light that will dim. And among those stars, one is our own sun, quietly burning, biding its time. Far in the future, on a planet that by then may only be a memory of what once was, the sun will paint the sky red in its final act, and scatter the elements of Earth and life back into space. Yet even as that seems like a melancholic fate, realize this: those same elements will not disappear. They will become part of something new. The atoms will rejoin the cosmic dance, perhaps to be incorporated into a new star, a new planet, a new life form in the distant future. In this, there is a kind of immortality, not of individual forms, but of the building blocks, the information, the stardust that cycles endlessly. We too are participants in this cosmic cycle. One day, every element of our bodies will return to the cosmos, perhaps drifting in space, perhaps locked in rock, perhaps pulled into the fires of a future star. And so, standing here, we are an ephemeral arrangement of eternal things. The stars died to give us life, and in time, we will give our elements back to stars. The light of a single star that died millions of years ago might be falling on your face as you look at the night sky. You are witnessing a star's elegy long after its death. But also, consider that the breath you just took contains argon atoms exhaled by countless beings before you, and carbon once formed in the core of a star, billions of years gone. The cosmos flows through us. In the end, as we reflect on dying stars, we find that their story is our story. A story of creation and annihilation, of despair and hope, of an endless cycle in a universe that itself may one day fade. It is a story that evokes humility and wonder. Humility in the face of the vast timescales and forces at play, and wonder at the fact that we can be here, pondering it all, products of the very phenomena we seek to understand. Every dying star whispers to the universe, I was here, I shone, I mattered, and I matter still, for I give of myself so that others may shine. In the grand darkness that will eventually engulf everything, the echoes of their light and the material they spread will be the legacy they leave behind, just as we hope in our brief lives to leave some legacy, some influence on the future. So the next time we look up at the stars, let us not only admire their present glory, but also honor their fate. They will perish, as all things do, but from their sacrifice comes the possibility of new light, new worlds, new wonders. In the death of stars, there is both the tragedy of an ending and the seed of creation. We journeyed from the gentle dimming of a single star to the cataclysmic collision of stellar remnants, across eons and into futures far beyond human imaginings. And through it all runs a common thread. In each finale, there is a quiet grace or a violent flourish that ensures the cosmos is never left unchanged. The dying star is not just an endpoint, it is a catalyst. As we conclude this cosmic tale, let's hold on to the image of starlight slowly fading, and then remember that even as it fades, somewhere else, perhaps due to that very fading, a new light will eventually spark. We are connected to those moments. We are the universe witnessing itself, understanding itself in bits and pieces. Our narrative ends where it began, with the light of a single star. Once upon a time, a star lived and died so that, much later, we could exist and ask why. One day, our sun will die, and from its death, new possibilities will arise that we cannot foresee. This knowledge is not cause for fear, but a gentle reminder of our place in a vast, ever-changing universe. Under the same cosmic sky, generations to come may tell the story of the star that gave them life, just as we tell the story of those that gave us life. In this way, the universe's endless cycle of starlight and darkness, of dying stars and rebirth continues, a story written across the cosmos in light and ash. And as long as there are eyes to see and minds to wonder, the legacy of dying stars will never truly fade. for we remember them in our very being. Every breath we take, every element that courses through our veins, is starlight remembered, a testament to the stars that lived and died to make our life possible. We inhale starlight, we exhale gratitude. The cosmos lives on through us as we live because of it. And when the night is darkest and one by one the stars above flicker out, we will still carry the memory of their light within us. For in a way, we are that light, given form and thought. This is what dying stars have given us, the chance to behold the universe's grand design, to feel wonder and to understand. Though the stars must die, their story and our story is unending. In our atoms, in our hearts, in the endless chain of cosmic creation, the light of the stars lives on. We are, all of us, starlight remembered, shining long after the source has gone out. In the silent darkness of space, a star dies. For a brief moment it outshines everything around it, a beacon of unimaginable brilliance piercing the void. What was once a steady pinprick of light in the night sky suddenly blossoms into a furious brightness, only to fade away and vanish. This is the paradox of a supernova, the explosive death of a star that looks to us like the appearance of a new one. In that instant of violent death, something new is born in its wake. We watch from our tiny world with both wonder and humility. Across the gulf of light, years, a distant sun has reached the end of its life and unleashed an energy beyond comprehension. It is an end in the most dramatic fashion possible, a final act that illuminates the cosmos. Yet it is also a beginning. The star's death throes scatter the heavy elements forged in its heart out into space, seeding the darkness with the ingredients for new stars, new planets, perhaps new life. In dying, the star becomes a cosmic phoenix. Its ashes enrich the galaxy and fertilize the universe. In a supernova's fleeting flash, we witness a cycle as old as the cosmos itself, creation and destruction entwined. The universe began with light, and in each stellar death, there is a small echo of that beginning, a burst of radiance, a flood of particles and atoms hurled outward to partake in future creations. Every one of us carries the story of these explosions in our bodies, the iron in our blood, the calcium in our bones, the oxygen we breathe. Those atoms were forged in stellar furnaces and scattered by stellar explosions long before the Earth coalesced. We are, quite literally, made of stardust, born from the remnants of ancient supernovae. So when we look up at the night sky, we are not just seeing stars, we are seeing memories. Each point of light is a story that may one day end in a supernova, as countless stars have before. Some of those stories ended eons ago, their light only now reaching us, bearing news of cosmic endings that were also cosmic beginnings. In the darkness between the stars, there are ghosts, expanding clouds of gas and dust that were once suns. And there are futures, nascent stars, forming in nebulae enriched by those past explosions. This is the tale of supernovas, at once an elegy and a celebration. It is the tale of how stars live, die, and transform the universe. It is a story written across millions of years, but observable in a single human lifetime as a sudden blaze in the sky. Together, we will journey through this story. We will witness the birth of a star and follow its life to the cataclysmic moment when the core collapses. We will explore the different kinds of supernovae that nature has devised and see how these brilliant events have touched human lives and imaginations throughout history. We will visit the most famous stellar explosions known to science and what they left behind. Beautiful nebulae, spinning neutron stars, perhaps even black holes that swallow all light. As we voyage through time and space in our collective imagination, we will see how supernovas are not random acts of destruction, but essential threads in the fabric of the cosmos. They are beacons, guiding our understanding of distant galaxies, engines driving the evolution of those galaxies, and perhaps harbingers of danger in our own cosmic neighborhood. They are the universe's great alchemists, forging heavy elements and sowing them far and wide. And in their afterglow, we find insight into the deepest mysteries of existence, including our own origins. Let us begin at the beginning of a star's life. Because to understand the death of a star, we must first understand how it lives. In the cosmic theater, every death scene is set by the long life that came before it. And so we step back to watch a star being born, knowing that in its birth lie the seeds of its demise and the promise of everything that will follow. The life cycle of stars. Before a star can die, it must live. Our journey begins in a vast, cold cloud of gas and dust, drifting in the galactic night, a stellar nursery waiting for a spark. In these dark, silent nebulas, gravity gradually draws denser clumps together. We imagine ourselves floating there as one particular clump, maybe a little larger than the rest, starts to collapse under its own weight. As it compresses, it heats up and begins to glow with a faint reddish light. We have witnessed the birth of a protostar, the first flicker of a new sun. In time, the growing protostar's core becomes hot and pressurized enough to ignite nuclear fusion. When its central temperature climbs to tens of millions of degrees, hydrogen atoms begin fusing into helium. With that first flash of fusion fire, a true star is born. It stabilizes, entering the long, steady middle of its life known as the main sequence. For millions to billions of years, this young star will shine, a blazing sphere of plasma held up against gravity by the continuous energy of fusion. In this stage, a delicate balance is struck. The inward pull of gravity and the outward push of radiant heat are in equilibrium. The star has found its rhythm, a stable heartbeat in the darkness. We look around and see countless stars on the main sequence, each with its own life clock ticking at a different rate. The massive ones, dozens of times heavier than our sun, burn their fuel extravagantly and live fast, shining hot and blue, white. They may spend only a few million years in this stable phase. Smaller stars, like our sun, burn more moderately and can shine for tens of billions of years. And the tiniest red dwarfs, barely heavy enough to ignite fusion, sip their fuel so slowly that they could outlive galaxies, trillions of years into the future. A star's mass is its fate. It determines how luminous the star is and how long it will live. As the eons pass, even the most enduring stars exhaust their primary fuel. In the core of a middle-aged star, like our sun, the hydrogen that once fused so plentifully is gradually converted to helium. When the core fuel runs low, the star begins to change. We watch as our once stable star starts to swell and redden, transforming into a red giant. Its outer layers puff outward, cooling and glowing a deep sunset hue. In its core, new fusion reactions ignite as helium fuses into carbon and oxygen. For a while, the star finds a new balance, but it is precarious, a sign of old age. For a star of modest size, this red giant phase is the prelude to a quiet death. When the helium is finally spent, such a star cannot muster the temperatures needed to fuse heavier elements. The core, now a hot ball of carbon and oxygen ash, begins to contract, while the outer layers become unstable. Gently, at least by cosmic standards, the star sheds its outer envelope into space, creating a glowing shell of gas called a planetary nebula. What remains at the center is the star's tiny, exposed heart, a white dwarf, no bigger than Earth, made of degenerate matter and slowly cooling over eternity. This is one possible end of the stellar life cycle, a hushed fading rather than a cataclysm. The once grand star becomes a faint ember, and the beautiful planetary nebula disperses into the interstellar medium over tens of thousands of years. But our focus is on a far more dramatic finale. one reserved for the giants among stars. Let us rewind a bit and follow the life of a truly massive star, say 10 or 20 times the mass of the Sun. These behemoths blaze blue, white, and live brief, brilliant lives. They race through their fuel, shining millions of times brighter than the Sun, and expending their core hydrogen in mere millions of years. When hydrogen runs out, the transition is anything but gentle. The core contracts and heats rapidly, and the star balloons into a red supergiant, enormous enough to engulf entire planetary systems. Betelgeuse, the red shoulder of Orion, is one such star nearing this final act, bloated, unstable, and nearing the end of its supplies. Inside such a red supergiant, the core temperatures soar high enough to fuse helium into carbon and oxygen, and then, with frightening speed, to fuse those elements into heavier ones. The star's life accelerates toward its conclusion. In successive stages, carbon burns to neon and magnesium. Neon burns to oxygen, oxygen to silicon, and silicon to iron. We imagine peering into the heart of this titanic star in its last million years and seeing something like the layers of an onion, concentric shells of burning elements, hydrogen in the outer layers, then helium, carbon, oxygen, and so on, all feeding an increasingly ferocious furnace at the core. At last, the star builds an iron core deep in its center. Iron is a fatal milestone for a massive star, for when nuclei fuse into iron, no energy is released. The process that sustained the star's outward pressure grinds to a halt, as if a beating heart has suddenly stopped. The core can no longer support the crushing weight of the star's immense outer layers. For a brief moment, a tense silence falls inside the star, the calm before an unimaginable storm. This is the end of the star's life as a normal star. In the iron core, which may be about the size of Earth, but with over 1 billion times Earth's mass, no more thermonuclear miracles remain to stave off gravity. The star has reached the brink of catastrophe. All the glorious millions of years of shining have led to this precipice. The outward light falters, the balance is undone, and gravity prepares to exact its final victory. In that final moment, the stage is set for a collapse and an explosion, the supernova we have been waiting for. The life cycle of the star, from birth in a nebula to maturity in the main sequence to bloated old age, has brought it inexorably to an existential crisis. What happens next will be the subject of the following chapter in our story. A chapter written in fire and fury as the star's core collapses and a supernova is born. The final act, core collapse. The end comes swiftly and without mercy. In the heart of our massive star, the iron core has grown to a critical mass, roughly 1.5 times the mass of our Sun, compressed into a sphere barely 50 miles across. At this extreme, the familiar laws of matter are on the verge of breaking down. Gravity, long held at bay by the energy from fusion, finally has the upper hand, and then, in a fraction of a second, the core buckles. We find ourselves in the core at the moment of collapse. Temperatures have soared to over 10 billion degrees and rising. The iron nuclei, pressed unbearably tight, begin to disintegrate into smaller particles. Electrons are driven into protons, turning them into neutrons and releasing floods of ghost, like particles called neutrinos. The core's atoms, once the powerhouse of the star, are now crushed into an ultra-dense ball of neutrons. In the span of a heartbeat, the core implodes, matter-free, falling inward at speeds approaching a significant fraction of light. The densities reach astronomical levels, higher than those inside an atomic nucleus. For an instant, the core is like a giant atomic nucleus itself, a sphere of neutrons about the size of a city. Suddenly, this collapse slams to a halt. The neutron core, essentially incompressible, resists further squeezing. It's as if the star has hit a concrete floor at nearly 1/4 the speed of light. the infalling material recoils. In that violent rebound, a powerful shockwave is born at the core and begins plowing outward through the star. But the shock alone is not yet the famous supernova explosion. It threatens to stall as it loses energy, tearing apart iron nuclei in its path. For a brief moment, it seems the star might simply collapse and swallow itself quietly. Then something extraordinary intervenes: the flood of neutrinos. Remember those neutrinos produced as electrons and protons were crushed together? In the turmoil of the collapsing core, billions upon billions of neutrinos are streaming out. Normally, neutrinos hardly ever interact with matter. They can zip through an entire star as if it were empty space. But here, in the densest environment the universe can offer outside of a black hole, even neutrinos begin to collide with matter. They deposit a stupendous amount of energy into the infalling layers just behind the shock front. This energy is the spark that revives the dying shockwave. With neutrino power added to the rebound, the shock roars back to life, surging outward with renewed fury. Now the star truly explodes. Within less than a second, the core collapse has transformed into an outgoing detonation. The shockwave tears through the star's layers from inside out. The overlying material, hydrogen, helium, carbon, all the way to the surface, is blasted into space at incredible speeds. The pressures and temperatures are so immense that new nuclear reactions ignite in the chaos, forging elements heavier than iron in fleeting moments of neutron bombardment. Gold, uranium, and dozens of other heavy elements are synthesized in these last violent seconds, like the final flourish of a master craftsman finishing a grand work. From outside, we would see nothing of this cataclysmic ballet until the shock breaks the star's surface. One moment, the star was a red supergiant, perhaps shining a bit erratically. The next moment, boom. The surface of the star is abruptly ejected, and a brilliant flash of light known as the shock breakout occurs. The star's outer layers, now unleashed, race outward as an expanding fireball, glowing a hot blue, white from the immense heat of the explosion. Within hours, the brightness swells dramatically. Within days, the exploded star becomes one of the brightest objects in its galaxy. A supernova has appeared where a familiar star used to be. At the core of this expanding fury lies the crushed remnant of the star, the ball of neutrons that survived the collapse. It is extremely small and dense. If its mass is below a certain threshold, it will settle as a neutron star, a city-sized stellar corpse. If it's more massive, nothing can halt its collapse, and it continues shrinking to become a black hole, an abyss from which no light escapes. But in either case, that core is no longer producing light. All the radiance of the supernova comes from the explosion's aftermath, from radioactive isotopes created in the blast decaying and heating the debris, and from the shock heating the star's outer layers as they expand. The dying star's final scream echoes across the electromagnetic spectrum. First comes a burst of neutrinos, an invisible herald racing ahead of the light. Then the light arrives, rapidly growing to a peak brightness that can rival an entire galaxy's output of stars. For weeks, too, months, the debris of the star glows intensely, powered by the decay of unstable isotopes forged in the fireball. We imagine watching from a safe distance as the shattered star's remains expand in a great spherical shell, cooling and dimming over time. Where once there was a mighty star, now there is a cloud of glowing ash, the embryonic form of a supernova remnant, and, hidden at the center, a compact new child of the cosmos born from the core's collapse. This is a core collapse supernova, the fate of massive stars. It is nature's grandest light show, a release of energy so colossal that for a short time, a single star's death outshines all the billions of stars in its galaxy. But not all supernovae follow this script. There is another type of stellar death, one that begins not with a massive living star, but with the quiet ember of a star that died long ago. Before exploring the remnants and outcomes of core collapse explosions further, we will take a detour to understand the other path to a supernova, the path of the white dwarf and the thermonuclear runaway. Two paths to destruction, Type 1 versus Type 2. Not all stars that go supernova do so in the same way. As astronomers studied the light from these stellar explosions, they found telltale differences. Some supernovae show signatures of hydrogen in their exploded debris. Others have no hydrogen lines at all. This was the first clue that there are two distinct paths to stellar oblivion. In the astronomical naming convention, those with hydrogen are called Type 2 supernovae, and those without are Type 1. We now understand that behind these spectral differences lie very different stories. The Type 2 supernova is the scenario we have just witnessed, the core collapse of a massive star that still had its hydrogen envelope at the time of explosion. The ejected material in a Type 2 supernova's spectrum reveals abundant hydrogen because the star was a red supergiant until the moment it died. These are the deaths of solitary massive stars, tearing themselves apart from the inside out. But what of the Type 1, the ones that mysteriously lack hydrogen? It turns out some stars die by borrowing a kind of second life, and then blowing themselves to pieces in a thermonuclear fury. Imagine a star, much like our Sun. After living out its life and quietly shedding its outer layers, it ends as a white dwarf, a small, dense stellar corpse composed mostly of carbon and oxygen, with no ongoing fusion. Normally, a white dwarf simply cools over the eons, but if this white dwarf has a close companion star, fate may have a more explosive plan. Picture a binary star system where one star is a white dwarf and the other is a living star. The white dwarf, though dead in the sense of fusion, still exerts strong gravity. It begins siphoning gas from its companion, pulling hydrogen and helium off the neighboring star's outer layers. The stolen gas accumulates on the white dwarf's surface, compressing and heating. For a while, this theft goes unnoticed on a cosmic scale. The white dwarf grows more massive, creeping toward a critical limit, about 1.4 times the mass of the Sun, known as the Chandrasekhar limit. This is the maximum mass that a white dwarf, supported only by the quantum pressure of electrons, can hold without collapsing. When the white dwarf approaches this threshold, something incredible happens. The pressure and temperature at its center become high enough to ignite carbon fusion in a runaway manner. Unlike a normal star, the white dwarf has no way to regulate this burning. It is essentially a giant bomb waiting for a spark. The carbon fusion spreads rapidly in a wave through the dwarf's interior, unleashing a titanic thermonuclear explosion. In a fraction of a second, the entire white dwarf is obliterated in one of the most brilliant fireworks the universe has to offer, a Type Ia supernova. This Type Ia supernova is fundamentally different from the core, collapse Type 2. It is not a star's core imploding under gravity. It is a prompt detonation, a nuclear bomb on a stellar scale. The white dwarf is entirely destroyed. No neutron star or black hole is left behind, only an expanding cloud of debris. Because the explosion comes from the sudden fusion of about a sun's mass of carbon and oxygen, it tends to produce a very consistent brightness each time. In fact, Type Ia supernovae act as standard candles for astronomers. Since they all reach roughly the same peak luminosity, we can gauge their distances by how bright they appear. We'll revisit this idea later when we see how such supernovae helped map the universe. For now, consider what the lack of hydrogen in the Type 1 spectrum means. A white dwarf has no hydrogen envelope. It lost all that long ago when its progenitor star shed its outer layers. So when it explodes, the debris shows no hydrogen lines. That's how we know a supernova was likely a Type Ia. Its light is missing hydrogen and often shows a distinctive signature of iron and nickel from the burned outcore of the white dwarf. There are also other subclasses of Type 1. For instance, Type Ib and Type Ic supernovae are actually massive star explosions like Type 2, but ones that shed their outer hydrogen before exploding. These usually happen in massive stars that blew off their envelopes via strong winds or interactions in a binary system. leaving a bare core to collapse. Thus, they are core collapse supernovae like Type 2, only stripped of their outer layers, so they masquerade as Type 1 by lacking hydrogen in their spectra. It can sound alphabet, soup confusing, but the essence is this. One path to supernova is a single, massive star collapsing under gravity. The other path is a smaller star, a white dwarf, blowing itself apart in a nuclear runaway. Both paths produce immense explosions, but their causes and outcomes differ. In one, a stellar core implodes and might leave a dense remnant. In the other, a stellar remnant detonates and leaves nothing substantial behind at its center. Understanding these two fundamental types gives us insight into the variety of cosmic fireworks we observe. Some supernovae announce the dramatic death of a lone giant. Others signal the demise of a long-dead star, reignited by a companion. Together, Type 1 and Type 2 supernovae account for nearly all the stellar explosions we see lighting up distant galaxies. With this framework in mind, we can better appreciate the events and remnants we are about to explore. Now let us step out of the theoretical realm and into human history. Long before we unraveled the astrophysical mechanisms, people witnessed supernovae in the sky without knowing what they were. They saw brilliant new stars appear where none had been before and grappled with their own interpretations. Our cosmic story now crosses paths with the human story as we look at supernovas through the eyes of those who saw them from Earth centuries ago. Supernovas in human history. Long before modern science unraveled the physics of supernovae, humans were witnessing these celestial events with naked eyes and recording their wonder and fear. To ancient sky watchers, the sudden appearance of a brilliant new star in the firmament was an astounding, often ominous event. The regular stars and planets followed known patterns, but a new star, a nova or guest star, as some called it, defied the idea of an unchanging heaven. It was as if the cosmos itself had spoken in a burst of light. One of the earliest recorded supernovae occurred in 185 AD. Chinese astronomers noted a strange guest star in the southern sky. It lingered for about 8 months before fading away, enough time for ancient observers to take careful notice. They dutifully recorded its position and its disappearance in official court chronicles. We now know that this was indeed a supernova, and modern astronomers have rediscovered the faint traces of its remnant about 8,000 light years from Earth. That ancient record, largely qualitative and couched in the language of omens, aligns with the physical evidence we see today of a Type Ia supernova explosion that occurred nearly 2 millennia ago. In late April of the year 1006 AD, a staggeringly bright guest star exploded into Earth's skies in the constellation Lupus. It ultimately reached an estimated visual magnitude of around 7.5, so bright that it was visible during the day. Observers across Eurasia marveled at it. Historical records say it cast shadows at night and was even visible during the day. The Egyptian astronomer Ali ibn Ridwan wrote that it was a large star which appeared in the south, having an enormous luster, far outshining Venus. We believe this was the brightest supernova ever observed by humanity in recorded history, what we now call SN 1006. People all over the world took note, and in some places it stirred fear or was interpreted as a portent. In North America, a possible record exists in an ancestral Puebloan pictograph, a depiction of a star next to a crescent moon on a rock wall in Chaco Canyon, which some have interpreted as a representation of this guest star. Though intriguing, such interpretations remain debated. Just a few decades after that, on July 4th, 1054 AD, all of Earth was treated to celestial fireworks as another new star appeared, this time in the constellation Taurus, the bull. Chinese court astronomers recorded that it was initially brighter than the moon and lingered in the sky for nearly 2 years before slowly fading from view. Unbeknownst to those observers, they were watching the birth of what we today call the Crab Nebula, the expanding remains of that exploded star. SN 1054 was likely a massive star's death. The memory of this event may also have been preserved outside East Asia. Medieval Japanese and Arabic records also mention a brilliant guest star around that time. And as mentioned, some interpret the rock art in the American Southwest as depicting the event. For medieval Europe, knowledge of these events was sparse. Europe in 1006 and 1054 was in the middle of the Dark Ages and early medieval period, and scholarly astronomy was less developed than in the Islamic world or China. Moreover, Aristotelian doctrine held sway. The heavens beyond the moon were thought to be immutable and unchanging. A bright new star did not fit that worldview and might even have been ignored or explained away by those who adhered to the idea of perfect, unchanging skies. Still, by the Renaissance a few centuries later, careful observers were starting to challenge that ancient dogma. In November 1572, sky watchers in Europe, including a young Danish astronomer named Tycho Brahe, were astonished by a brilliant star in the constellation Cassiopeia, where no star had been seen before. Tycho diligently observed this nova stella every night, measuring its position relative to the fixed stars. He found it showed no parallax, meaning it was far beyond the moon, out among the stars, which directly contradicted Aristotle's notion of an unchanging celestial realm. Tycho's supernova shone as bright as Venus for weeks. We now suspect SN 1572 was a Type Ia thermonuclear supernova, the kind involving a white dwarf. Modern studies of the remnant show no neutron star at the center, consistent with a Type Ia where the star was obliterated. For Tycho and his contemporaries, the event was pivotal. His observations, published in a work titled De Nova Stello, were a key piece of evidence that the heavens do change, helping pave the way for the new astronomy of Copernicus, Galileo, and Kepler. To the public and religious authorities, the new star was often seen as an omen. To Tycho, it was a scientific revelation. Only 32 years later, in October 1604, another brilliant star burst forth, this time in the constellation Ophiuchus. The famous astronomer Johannes Kepler observed it closely and wrote a book about it. SN 1604, or Kepler's supernova, became brighter than all stars and planets in the sky at its peak. Like Tycho's, it had no measurable parallax, further driving the nail into the coffin of the Aristotelian crystalline spheres theory. It was the last supernova observed in our Milky Way with the naked eye. Modern astronomers have studied Kepler's supernova remnant and, based on its characteristics, believe it too was likely a Type Ia event. Thus, the two great Renaissance supernovae were both thermonuclear explosions of white dwarfs, yet their appearance at critical moments in history had enormous impact on human thought, marking the end of an era when the cosmos was thought to be static and perfect. Throughout human history, only a handful of these new stars have been recorded, but each left an imprint on culture and science. From Chinese astrologers linking them to dynastic fortunes, to European scholars using them to question classical doctrines, supernovae have occasionally influenced the course of human thought. Most of the time, the stars live and die unseen. But when one does announce itself to us, it rarely goes unnoticed. These events also gradually built a bridge between myth and science. Each recorded observation, from 185 AD to 1572 to 1604, added a piece to the puzzle that modern astrophysicists would later assemble with telescopes and physics. Today, we can return to those historical supernovae with our scientific tools. The Crab Nebula still glows in our telescopes, and at its center, a pulsar, a rapidly spinning neutron star, blinks 30 times a second, the collapsed core left from that explosion. The remnants of Tycho's 1572 and Kepler's 1604 supernovae have been detected as expanding shockwaves in space, and careful measurements of their light, echoes, and debris composition have helped identify their type. In this way, the observations of long-ago sky watchers connect directly to the science we conduct now. The people of the past saw supernovas without understanding their true nature, but they carefully noted their appearance and timing. We, following in their footsteps, can point our instruments to those same locations centuries later to learn the why and how. It is a beautiful continuity of curiosity. Now, with the historical context in mind, let's focus on a few of those famous supernovae that have become legends in both astronomy and culture. The ones whose names have been mentioned. The mysterious guest star of 1054 that created the Crab Nebula. The brilliant new stars observed by Tycho and Kepler that altered the course of astronomy. And a much more recent stellar explosion that heralded the dawn of a new era in space observation. These are supernovas that stand out like beacons in human history's record of the sky. Witnessing great explosions, famous supernovas. Across the ages, certain supernova events stand out as especially notable, either for their brilliance, for the insights they gave us, or for the lore that surrounds them. Let us revisit a selection of these cosmic spectacles in more detail, to feel what it might have been like to witness them and to understand what they have taught us. SN 1054, the Crab Nebula's birth. It is summer in the year 1054. On a July night, people around the world gaze upward to find a startling new light in the heavens, near the starry outline of Taurus the Bull. Chinese astronomers in the Song dynasty record that it is as bright as Jupiter, eventually even brighter, visible in the daytime for weeks. They call it a guest star, and note its gradual fading over nearly 2 years. What those observers see is the death of a massive star, roughly 6,500 light years away. Today, when we point a telescope at that same spot, we see the Crab Nebula, a sprawling tapestry of filamentary gas and dust expanding in space. At its center, a tiny pulsar flashes 30 times a second like a cosmic lighthouse. This pulsar is the collapsed core of the star that exploded. The Crab Nebula, with its eerie tendrils of glowing gas, is essentially frozen fireworks from 1054, still expanding at thousands of kilometers per second. Studying it across different wavelengths has given astronomers invaluable insight into how supernova debris evolves and how neutron stars behave. One can imagine the awe of ancient sky, watchers seeing the initial explosion, not knowing that before them was the creation of a beautiful nebula that later astronomers would come to understand and marvel over. The Crab Nebula stands as a bridge between human history and astrophysics, a guest star turned enduring monument in the sky. Tycho's star of 1572. Fast forward to November 1572, Denmark. Tycho Brahe, returning from his evening walk, looks up and is astonished to see a brilliant star in the otherwise familiar pattern of Cassiopeia. A star that simply was not there the night before now shines proudly. Tycho quickly organizes systematic observations, measuring the star's position relative to the moon and known stars night after night. He finds, to his wonder and intellectual delight, that the new star exhibits no parallax, no shift against the distant star background from Earth's orbit. It must lie among the fixed stars, far beyond the moon, proving the heavens are not immutable. Tycho writes about this discovery in detail. The star shines with the brightness of Venus, then slowly fades over about 16 months. We now know SN 1572 was a Type Ia supernova, a thermonuclear explosion of a white dwarf star in a binary system. Its remnant, seen with modern telescopes, is an expanding cloud of gas with no pulsar or neutron star inside. Tycho's careful work on this supernova provided crucial evidence that the Aristotelian cosmos was flawed. It marked a paradigm shift. the universe beyond Earth was dynamic and changing. Culturally, Tycho's new star challenged theologians and philosophers. Scientifically, it propelled the likes of Kepler and Galileo to further question cosmic dogma. It is poignant that a dying star, which had likely been dead for thousands of years before its light reached Earth, helped spark the birth of modern astronomy. Kepler's supernova of 1604. Just 32 years after Tycho's event, the cosmos provided another spectacular display. In October 1604, in the constellation Ophiuchus, a new star blazed forth. It reached magnitude 2.5, outshining every star and planet in the night sky. The great mathematician and astronomer Johannes Kepler observed it extensively. People across Europe saw it. Kepler, much like Tycho, found that it showed no parallax. By this time, the Copernican view of the solar system was gaining traction, and Galileo would soon turn a telescope to the heavens. Kepler's supernova, though a brilliant apparition, was the last such to be observed in our Milky Way to date. Modern analysis of its remnant, using space telescopes, indicates it was likely a type Ia as well. Kepler compiled observations of the 1604 supernova, noting its color changes and steady decline in brightness over a year and a half. Kepler's work, published in De Stella Nova, along with Tycho's earlier nova, cemented the idea that the heavens evolve. Philosophically, it shook the last resistance to the notion that change and decay occur in the celestial realm just as on Earth. After Kepler's star, no new stars were seen in our galaxy, so these two Renaissance supernovae stand out as heralds of a new worldview. They bookend the 16th century's scientific revolution, and each bears the name of the astronomer who studied it because their observations were so influential. Supernova 1987A, a modern spectacle. For more than 300 years after Kepler's 1604 event, no supernova bright enough to see with the naked eye was observed, though many undoubtedly occurred hidden behind interstellar dust or on the far side of the galaxy. Then, on February 24, 1987, something historic occurred. A brilliant new star was spotted in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, visible to the naked eye in the southern hemisphere. This was the nearest supernova since Kepler's about 168,000 light-years away. Supernova 1987A was extraordinary, not just for being visible to modern humans, but for being studied with modern scientific tools. Prior to the visible light, detectors deep underground in Japan, the US, and the Soviet Union picked up a flurry of neutrinos, 24 neutrinos in total, arriving within a 13th of a second window, just hours before the supernova was seen. These ghostly particles were emitted from the collapsing core of the star and provided direct confirmation of the core collapse mechanism we described. It was the first time humanity caught neutrinos from beyond the solar system, and they came from a dying star's core. When the light arrived, telescopes around the world and above it turned to watch SN 1987A. They saw the rise and fall of its light, measured the nuclear isotopes powering its glow, and observed its debris expanding. SN 1987A turned out to be a bit of a surprise to theorists. The star that exploded was not a red supergiant, but a blue supergiant, a hotter, more compact star. It had likely been a red supergiant earlier, but perhaps merged with a companion or shed mass in a complex way that left it blue at the time of collapse. The star left behind a striking arrangement of glowing rings, material it had ejected in earlier epochs, which the supernova's blast wave has since been colliding with, producing a fireworks show of its own as the rings brighten in response. We are still observing 1987A decades later. It's a living laboratory for supernova physics. So far, no neutron star has been definitively seen inside, leaving a tiny bit of mystery. But we detected the cobalt and titanium produced in the explosion, confirming models of how elements are forged. We witnessed the light from the blast echo off interstellar dust, giving us different perspectives of the event. In short, 1987A was like an astrophysical Rosetta Stone, offering answers to long-standing questions and posing new ones. For people around the world in 1987, especially those in places like Australia or Chile, who could see the large Magellanic Cloud in their night sky, the appearance of a new star was thrilling. Unlike in 1572, it didn't spark fear or philosophical crisis. Instead, it sparked celebration among astronomers and curiosity among the public. At observatories, champagne bottles were uncorked when the first neutrinos were confirmed and the optical counterpart was found. Humanity had waited centuries to see such an event up close, and now we finally had front row seats. SN 1987A inaugurated the era of multi-messenger astronomy, using not just light, but particles like neutrinos to study cosmic events. And it came just as computing and telescope technology allowed us to capture it in unprecedented detail. From the ancient guest star of 1054, recorded by Chinese astrologers, to the modern supernova of 1987, observed with neutrino detectors and space telescopes, our understanding has grown immensely. Each famous supernova has left an enduring legacy. The Crab Nebula's pulsar confirmed the existence of neutron stars. Tycho's and Kepler's observations helped dismantle the old cosmic order. SN 1987A gave direct confirmation of theory and a wealth of data on how supernovae work. They are shining milestones on our journey to comprehend the universe. Having witnessed what happens when stars explode, we turn now to one of the most profound consequences of these events: the creation of the very stuff that makes up planets and people. In the violent cauldrons of supernovae, elements are forged that otherwise would not exist. This is the story of nucleosynthesis, the cosmic alchemy carried out in stellar life and death. Stardust and elements, nucleosynthesis in supernovae. Every atom in our bodies has a story that stretches back to the stars. The golden ring on a finger, the calcium in our bones, the iron in our blood, all were forged in cosmic furnaces and explosive crucibles. Supernovae are not merely spectacular light shows, they are also the universe's great alchemists. To understand how, we must look at what happens deep inside stars and during those final explosive moments of their deaths. Throughout a massive star's life, its core is a fusion factory, sequentially forging heavier elements out of lighter ones. Hydrogen fuses into helium in the star's youth. Later, helium burns into carbon and oxygen. Then, in truly massive stars, oxygen, neon, magnesium, silicon, sulfur, and more in turn undergo fusion as the star approaches old age. This sequence of fusion reactions builds up the periodic table within the star, but it stops at iron. As we saw, once iron accumulates in the core, no further fusion can release energy. Without energy output to support it, the iron core succumbs to gravity and collapses, triggering a core collapse supernova. When a supernova explosion occurs, it not only liberates these pre-made elements by blowing the star apart, it also creates new ones in the heat of the blast. Consider the core, collapse supernova of a massive star. As the shockwave rips through the star's layers, the extreme heat and flood of neutrons trigger a flurry of nuclear reactions in the surrounding material. In mere seconds, elements heavier than iron are synthesized via rapid neutron capture a process called the R process. The collapsing core unleashes an enormous number of neutrons, and atoms riding the shockwave absorb these neutrons in rapid fire succession. These neutron-heavy nuclei then undergo radioactive decay into stable elements. In this way, elements like iodine, gold, platinum, uranium, roughly half of all elements heavier than iron, are created in the cauldron of a single supernova explosion. Meanwhile, in a Type Ia supernova, a different kind of nucleosynthesis occurs. The furious burning of carbon and oxygen into a range of intermediate mass elements, particularly a lot of nickel and iron. Type Ia supernovae are prolific producers of iron group elements. In fact, the iron that makes our blood red and the nickel and cobalt in steel are spread through galaxies largely by type Ia supernovae. Without those explosions, iron, the heaviest element that normal stellar fusion can produce in quantity, would remain locked in stellar cores or white dwarfs. Supernovae act as cosmic salt shakers, scattering these elements into the galactic soup. Think of a supernova as a cosmic seed, spreader. The heavy elements created over the star's life, and in its explosive death, are hurled into space at thousands of kilometers per second. In the aftermath, what was once the star's core might be a neutron star or black hole, but all its outer material, now enriched with a bouquet of heavy elements, mixes into the wider interstellar medium. Over millions of years, that gas will drift, cool, and mingle with other gas clouds. When new stars eventually form from those clouds, they inherit that enrichment. Planets condense from the leftover dust and gas around those new stars, and in some of those planets, life might one day arise, incorporating the atoms that were forged in a star long ago. To put it poetically, supernovae are the universe's way of taking matter cooked in one star's kitchen and delivering it as raw material for new worlds. In the early universe, before any stars had lived and died, there were only the lightest elements, hydrogen, helium, and trace amounts of lithium. The very first generations of stars were born from this pristine gas. Many of those first stars likely died in powerful supernovae that enriched their surroundings with the first heavy elements. Each subsequent generation of stars thus had more metals available. Our Sun was born from a cloud already seeded by countless prior supernovae. That's why Earth has an iron core and rich chemistry, and why life here can have elements like carbon, nitrogen, phosphorus, and so on. All those elements were gifts from stars that died before the Sun was born. Carl Sagan famously said, "We are made of star stuff." And this is not just metaphor, but scientific truth. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in the apple pie we might eat. These atoms were forged in stellar interiors and in the titanic explosions of supernova. We carry within us the ashes of long dead stars. Every time you hold a piece of gold jewelry or take a breath of air, you are touching remnants of a supernova's fury. In a very real sense, supernovae are our ancestors. They sculpted the elemental, abundances of our galaxy. They made possible the chemistry that begot life. Realizing this connection can change the way we see a starry night. The sky is no longer just a beautiful backdrop. It's our ancestral home. We have stardust in our veins. Supernovae ensure that the universe is chemically rich and ever changing, rather than static and composed of only the simplest elements. A universe without supernovae would be a dull place. No rocky planets, no breath of air, likely no life. Having explored how supernovae forge the ingredients of planets and people, let us now examine what becomes of the stars themselves after the blast. What of the core that collapsed? That neutron, rich ball that was left behind? It may become one of the strangest objects in the universe. Let's meet the exotic corpses of massive stars, the neutron stars and black holes that emerge from the wreckage of supernovae. The corpses of stars, neutron stars, and black holes. After the immense explosion of a supernova fades, after the debris is cast into space, something often remains at the center. An ultra-dense stellar corpse, the condensed memory of the star that was. In the case of a core collapsed supernova, the core's collapse is halted by forces of quantum physics, leaving behind either a neutron star or, if the star was hefty enough, a black hole. These remnants are as fascinating as the explosions themselves, for they are among the strangest objects in the universe. Neutron stars, the spinning cinders. Imagine compressing the Sun, 333,000 Earth masses, into a sphere about 20 kilometers across, roughly the size of a city. The crush of gravity is so extreme that atoms cannot survive. Electrons have been rammed into protons to form neutrons, and matter as we know it is essentially transformed into a giant atomic nucleus. This is a neutron star. A sugar cube-sized amount of neutron star material would outweigh a mountain. The gravity at its surface is so strong that if you dropped a marshmallow from 1 meter above a neutron star, by the time it hit the surface, it would strike with the energy of an atomic bomb. These mind-bending facts belie the humble name, neutron star, but they are the reality of what a massive star's core becomes after a successful supernova explosion. Neutron stars often reveal themselves as pulsars, objects that emit beams of electromagnetic radiation that sweep around as the star rotates, like beams from a lighthouse. The first pulsar was discovered in 1967 by Jocelyn Bell. At first it was so regular that it was jokingly nicknamed LGM-1, hinting at the intrigue it caused. We now know pulsars are rapidly spinning neutron stars with intense magnetic fields, whipping around perhaps dozens or hundreds of times per second. The Crab Nebula's heart, for instance, is the Crab pulsar, spinning about 30 times a second, a lighthouse flashing in the wreckage of the 1054 supernova. Every pulse we receive is a rotation of that tiny neutron star, which carries on the legacy of the once mighty star by flashing its cosmic heartbeat centuries after the star's explosive death. Some neutron stars are even more extreme, magnetars, with magnetic fields 1,000 times stronger than a typical pulsar, capable of emitting flares that can disrupt Earth's ionosphere from tens of thousands of light years away. These bizarre objects are variations on the theme of neutron stars, matter in its most compact, stable form, holding perhaps up to 2 or 3 solar masses in that ultra-dense sphere. They gradually cool and slow down over time, but for many millions of years, they can spin rapidly and power energetic emissions, effectively signaling their presence to the cosmos. In a very real way, a neutron star is the remaining core of a star, still there after the supernova, not shining by fusion, but often emitting energy as it slows down, the stellar core's ghost, left haunting the site of the explosion. Black holes, the silent tombs. If the collapsed core of a star exceeds a certain mass, not even the pressure of neutrons can halt the collapse. In that case, gravity wins absolutely, and the core continues to shrink beyond the neutron star stage. It effectively vanishes from view, leaving behind a gravitational well so deep that not even light can climb out. A black hole is born. What remains is an object perhaps only a few kilometers wide, but containing more mass than our Sun. An object with no surface, only a point of no return, called an event horizon. Inside that boundary, space, time is curved into a pit from which nothing that falls in can escape. The core of the star has become a literal hole in the fabric of reality. Black holes were once theoretical curiosities, sprung from Einstein's general relativity equations, and considered by some to be too absurd to be real. Today, we have overwhelming evidence of their existence. Many stellar black holes announce themselves indirectly, often by interacting with a companion star. Gas from the companion may spiral into the black hole, heating up and emitting powerful X-rays before it vanishes across the event horizon. Cygnus X1, an X-ray source discovered in the 1960s, was the first strong black hole candidate. It likely formed from a massive star's collapse. Now we know many such X-ray binaries harbor black holes. Additionally, the ripples of gravitational waves detected in the past few years by observatories like LIGO and Virgo have come from mergers of stellar mass black holes, offering yet another confirmation that these dark remnants are out there. To stand on the surface of a neutron star or near a black hole's horizon is to confront the ultimate victory of gravity. Time itself behaves oddly in these realms. A clock on a neutron star's surface would tick significantly slower relative to one far away due to gravitational time dilation. Near a black hole, that effect becomes even more extreme. Time essentially stops at the horizon from an outside perspective. These effects, though counterintuitive, have been measured in weaker gravity regimes and match our theoretical predictions. In simpler terms, a neutron star or black hole is the outcome of a star's final battle with gravity. The star's core, unable to hold itself up, imploded and then found a new equilibrium as one of these exotic objects. They are the cinders or tombstones left after the brilliant supernova fire has gone out. Yet they are far from inert lumps. Neutron stars can light up their surroundings with beams of radiation or intense magnetic fields, and black holes, when fed by infalling gas, can become the engines for powerful X-ray sources or micro-quasars. Even in death, these stellar remnants can profoundly affect their environment. When we gaze into the night with radio telescopes or X-ray eyes, we occasionally hear the ticking of pulsars or see the flickering high energy glow of accreting black holes. Each is a supernova afterstory, the quiet, persistent end, note to a star's life. In the grand narrative, a massive star lives, explodes, and then either as a neutron star or black hole remains as a kind of monument. It's humbling to realize that the universe is littered with these tiny, dark remnants, hidden endpoints of countless stellar lives. We have now followed the star from cradle to grave, born in a cloud, shining steadily, dying in an explosion, and leaving behind a strange new object. Let us cast our eyes outward again to the expanding remnants of those explosions and see what becomes of the scattered star stuff itself. Supernovae do not merely vanish, they leave behind remnants that continue to glow and evolve, creating some of the most beautiful and intriguing sights in the cosmos. Ghostly echoes, supernova remnants. Long after the blinding flash of a supernova has faded from the sky, an ethereal apparition remains, the supernova remnant. These are vast, expanding clouds of debris, the scattered ashes of a star, still glowing from the energy of the explosion and the radioactive elements within. Supernova remnants are like cosmic smoke rings, beautiful, complex, and evolving over time, marking the spot where a star met its end. If we could watch a supernova remnant in fast forward, we'd see an almost spherical shockwave racing outward, plowing into the surrounding interstellar gas. Behind the shock front trails the tattered debris of the star, a mix of elements and newly formed radioactive isotopes, forming intricate structures as it interacts with itself and the environment. Immediately after the supernova, this cloud is extremely hot and shines brightly in X-rays. Over centuries and millennia, it expands and cools, beginning to radiate at optical wavelengths as well, and later in radio waves. Filamentary shapes appear, tangled ropes and sheets of gas shaped by magnetic fields and variations in density. One of the most famous remnants, the Crab Nebula, is a sight to behold even in a small telescope, a faint oval patch of light with subtle filament patterns. Long exposure photographs and modern space telescopes reveal those filaments in exquisite detail. Tendrils of glowing red, orange, where cooler gases like hydrogen and nitrogen emit visible light, interlaced with a bluish haze of electrons spiraling in the pulsar's magnetic field. The Crab Nebula is effectively powered from within by its pulsar. The neutron star's rotational energy keeps pumping out particles and fields that energize the nebula, making it shine far longer than it would from the explosion's initial heat alone. It's as if the remnant is a living organism with a beating heart that refuses to let the glow die out. Another remarkable remnant is Cassiopeia A. Although its originating supernova around 1680 was not widely observed, Cass A is a young remnant about 350 years old, and high-resolution images show an asymmetric, lumpy shell of gas about 10 light-years across. It's rushing outward at thousands of kilometers per second. By studying Cass A, scientists have gleaned insights into how the supernova explosion might have been irregular, not a perfectly symmetric blast, but one that ejected knots of material in some directions more than others. Cass A's debris is rich with elements like oxygen, sulfur, and silicon, clearly marking it as the remains of a massive star. In the center lies a faint neutron star, cooling in quiet isolation. The ghost of the star is not at rest. It's expanding and colliding with its surroundings, sending out shockwaves that heat the interstellar medium and even accelerate cosmic rays that zip through our galaxy and occasionally reach Earth. Supernova remnants can be breathtakingly beautiful. The Veil Nebula in Cygnus, for example, is the remnant of a supernova roughly 8,000 years ago. It now spans about 3 degrees of the sky as a wispy lacework of ionized gas. Through a telescope, parts of it appear as delicate filaments, so thin and gossamer that one can scarcely imagine the violent event that created them. These filaments are shock fronts seen edge-on, where the shell of the remnant is plowing into interstellar space and causing the gas to glow. What was once a catastrophic blast has, over millennia, become a faint, ghostly veil decorating the sky. Beyond their beauty, supernova remnants are profoundly important to the ecosystem of the galaxy. As the remnant expands, it sweeps up and stirs the interstellar medium, mixing the new heavy elements from the explosion into the cosmic clouds. This enriched material will one day become part of new stars and planets. The shockwaves can trigger the collapse of nearby gas clouds, perhaps inducing new stars to form, so one star's death can sow the seeds for the birth of others. At the same time, remnants inject energy into the galaxy's gas, heating it and driving turbulent motions that can inhibit immediate star formation elsewhere. This feedback helps regulate how galaxies evolve, preventing them from turning all their gas into stars at once. Over tens of thousands of years, a supernova remnant will gradually dissipate. Its shock slows to the speed of sound in the surrounding medium and eventually merges with the general interstellar environment. By then, the heavy elements are well blended into the galactic reservoir. Only faint traces might remain, perhaps slightly higher concentrations of certain elements in that region of space, or cosmic ray particles that were accelerated by the remnant's shock still wandering the galaxy. Thus, a supernova remnant is the intermediate chapter of the story, between the violent death and the eventual recycling of the star's substance into new cosmic structures. It's the long, fading echo of the supernova's shout. By reading the glowing wisps and shock fronts, scientists can decode details of the explosion, how fast the material is moving, what it's made of, and how it's interacting with its surroundings. Even long after a star has died, its remnant continues to tell its story. In every supernova remnant, we see a snapshot of change in action. They are elegant reminders that even after catastrophic destruction, there is quiet creation and transformation. The scattered atoms will someday cool and perhaps gather again in dark nebulae, ready to form the next generation of stars. In that way, a ghostly remnant is not an end, but a bridge to new beginnings. Stepping back from individual remnants, we consider the grand scale once more. Supernovae, whether near or far, serve as brilliant beacons in the cosmos. Their light and energy travel across vast distances, sometimes allowing us to measure and understand the universe itself. In the next section, we'll explore how these stellar catastrophes become cosmic lighthouses and what they have revealed about the space between the galaxies and the fate of the universe at large. Cosmic beacons, light across the universe. Supernovae are not only agents of cosmic recycling, they also serve as signposts on the grandest scales. When a star explodes, it becomes, for a few weeks, one of the most luminous objects in the universe. A single supernova can outshine an entire galaxy of billions of stars. This extraordinary brilliance means that supernovae can be seen across immense distances, allowing astronomers to use them as cosmic beacons or lighthouses. By observing supernovae in remote galaxies, we can measure those galaxies' distances and probe the expansion of the universe itself. Among all supernovae, the type Ia have proven especially valuable in this regard. Because a type Ia results from a white dwarf reaching a critical mass and undergoing a thermonuclear explosion, the amount of energy released is fairly uniform from one event to another. In more practical terms, most type Ia supernovae reach about the same peak absolute luminosity, like bulbs of nearly the same wattage. If we observe a type Ia in a distant galaxy and measure how bright it appears, we can compare that to the known true brightness and deduce its distance. A classic use of the inverse, square law of light. This is why type Ia supernovae are termed standard candles. In the late 20th century, astronomers began using these standard candles to chart the universe. They painstakingly observed type Ia supernovae in far-away galaxies, billions of light years distant. By doing so, they aimed to measure how fast the universe was expanding at different times in the past. The expectation was that the expansion should be slowing over time as gravity tugged on galaxies. But the supernova beacons told a different story. In 1998, two independent teams analyzing distant type Ia supernovae made a shocking discovery. Those supernovae were dimmer than expected in a decelerating universe. The simplest explanation was that the expansion of the universe has been speeding up, an acceleration driven by some mysterious force or energy inherent to space itself, later dubbed dark energy. It was a revelation that earned the 2011 Nobel Prize in Physics for the team leaders. Think about that. By observing the dying flashes of stars in galaxies halfway across the observable universe, we gleaned insight into the fundamental behavior of the cosmos on the largest scale. Each supernova that appeared in those distant galaxies, tiny dots of light on telescope images, carried within it the information needed to trace the history of cosmic expansion. The lives and deaths of stars, recorded as brief flickers in the night, became evidence for a new ingredient of the universe that now appears to dominate its fate. Supernovae also help us measure distances closer to home and map the three-dimensional structure of the universe. Even before the discovery of cosmic acceleration, astronomers used type Ia supernovae to refine the Hubble constant. By comparing distances from supernovae with the redshifts of their host galaxies, they calibrated the relationship between redshift and distance. This led to a better handle on the size and age of the universe. To this day, monitoring supernovae in distant galaxies remains crucial for improving our understanding of the universe's expansion history and for probing the nature of dark energy. Apart from cosmology, supernovae act as beacons that illuminate their local environment. As their light travels through space, it can be absorbed or re-emitted by any intervening gas or dust. By studying the spectrum of a supernova, we can detect absorption lines from elements in the host galaxy or in between galaxies. In one famous case, light from a distant supernova passed through the vicinity of a foreground galaxy cluster and was gravitationally lensed, producing multiple images of the supernova that reached Earth at different times. Astronomers observed one image of that supernova and, by understanding the lensing delay, successfully predicted when the second image would appear a couple of years later, and they saw it right on schedule. This kind of phenomenon turns supernovae into probes of the distribution of matter in the lensing clusters. Even without such exotic effects, every supernova in a distant galaxy provides clues about that galaxy, its composition, its star formation, history. When a massive star explodes in, say, a galaxy tens of millions of light years away, We detect it and thus learn that this galaxy is actively forming stars. Supernova surveys have catalogued thousands of supernovae in all types of galaxies, revealing patterns. For instance, Type 2 and Type IB/C supernovae occur only in galaxies with ongoing star formation. You won't find a massive star supernova in a quiescent elliptical galaxy, because such galaxies no longer have massive young stars. On the other hand, Type Ia supernovae occur in both star-forming galaxies and old elliptical galaxies, since every galaxy has some population of binary white dwarfs or old stars that can produce them. The sheer number of supernovae now catalogued has allowed us to identify rare subclasses and see subtle differences. We found peculiar types often by catching them in other galaxies. No two supernovae are exactly alike. Each explosion has its quirks, but they cluster into families that we can study statistically. And all of this has been possible because the universe provides an endless supply of distant supernovae, and we've developed the technology to monitor the sky systematically. Technology is rapidly advancing this field. The Vera C. Rubin Observatory in Chile, with its legacy survey of space and time, is expected to discover on the order of 10,000 supernovae per year in the coming decade. It will effectively make a high-definition movie of the optical sky, catching transient events like supernovae on a nightly basis. We will have supernova light curves and spectra in amounts previously unimaginable, likely uncovering new oddball explosions and further refining the use of supernova as cosmic yardsticks. There's also something profoundly moving about seeing supernovae in distant galaxies. It drives home the point that the life and death of stars is a universal saga. When you see a tiny, bright dot on an image of a galaxy tens of millions of light years away, knowing it's the death throe of a star, possibly someone else's sun in that galaxy, you feel an intimate connection with a distant part of the universe. These events link us with other galaxies, not just in a physical sense, but in a narrative sense. The story of stars and supernovae is a thread that runs through the cosmos, binding our Milky Way to the remotest spiral. From the closest supernova observed with the naked eye in centuries to the farthest detected by our most sensitive telescopes, each is a flash of enlightenment across space and time. Through them, the universe has communicated its nature to us. They have been beacons not only of light, but of knowledge, guiding us to understand cosmic distances, the expansion of space, and the history of galaxies. We have now covered supernovae from the tiny scale of atomic nuclei in a collapsing core to the vast scale of the accelerating universe. It seems fitting, as we near the end of our journey, to reflect on what it all means, how the death of stars is connected to the existence of life, and what philosophical insights we can glean from the cycle of stellar death and rebirth.
Danger in the sky, the threat of supernovas.
Supernovae captivate us with their brilliance and enrich us with their stardust, but they also remind us that the cosmos can be dangerous. A star's death is not only a spectacle, it unleashes a storm of radiation and high-energy particles that can have profound effects on its surroundings. If such an explosion happened close enough to Earth, the consequences could be severe for our planet's biosphere. Have supernovae ever affected life on Earth? Could they in the future? These questions take us from cosmic wonder to an edge of concern. Fortunately, the odds of a supernova occurring very near Earth in our lifetimes are low. Our Sun is not massive enough to explode, and among the nearest stars, none within the critical distance are likely to go supernova soon. The general consensus is that a supernova closer than about 25 to 50 light years could pose a serious threat, primarily by bathing Earth in intense high-energy radiation and a barrage of cosmic rays. The immediate effect of such radiation on Earth's atmosphere would be to erode the ozone layer that shields us from the sun's ultraviolet rays. With the ozone layer damaged, harmful solar UV would flood the surface, potentially causing mass die-offs, especially in marine ecosystems where plankton, the base of the food chain, are vulnerable to UV. Scientists have searched for fingerprints of past supernova effects on Earth. One intriguing find lies in ancient seabed deposits. An excess of the radioactive isotope iron in sediment layers dated around 2,003 million years old. Iron 60 is produced in supernovae and has a half-life of 2.6 million years, so finding it on Earth's surface implies a relatively recent nearby supernova. Indeed, some studies suggest that one or more supernovae occurred about 2.5 million years ago at 150 light-years away, possibly affecting Earth's climate or contributing to minor extinctions. Another study links increased radiation levels to a minor extinction at the end of the Pliocene epoch, speculating a supernova as a cause. While these connections remain under investigation, they highlight that Earth is not completely immune to astrophysical events. If a supernova happened, say, within 30 light-years, the radiation pulse could cause a mass extinction by wrecking the ozone layer and bombarding life with UV. The geological record does show some unexplained extinction events that some scientists have playfully speculated might be due to nearby gamma, ray bursts, or supernova. Which nearby stars could pose such a threat? The good news is, none of the very closest stars are of the type to explode soon. The nearest massive stars are dozens to hundreds of light-years away. Betelgeuse, the red supergiant in Orion, often comes up in discussion. It's about 650 light-years away. When Betelgeuse does explode, it will likely put on a spectacular show, potentially bright enough to see in daytime, but it's too distant to harm Earth aside from perhaps some subtle effects on our upper atmosphere. Candidates often mentioned include stars like Antares, or more significantly, a star system called IK Pegasi, which includes a white dwarf that could become a Type Ia supernova in the far future. However, by the time IK Peg's white dwarf accretes enough mass from its companion to explode, it will likely have drifted farther from us. Another potential danger comes from gamma, ray bursts, extremely energetic jets that can accompany certain supernova-like events, especially the collapse of an especially massive, rapidly rotating star into a black hole. If a gamma ray burst were pointed directly at Earth from a few thousand light-years away, the focused beam of gamma radiation could be devastating. Even from much further than the supernova's general radiation would be dangerous. Fortunately, such GRBs are rare, and the Milky Way is big. No known GRB progenitor is close enough and aimed at us to cause concern at present. One speculative idea is that a GRB might have caused the Ordovician mass extinction 450 million years ago, but this remains unproven and perhaps unprovable. So, while the risk is never zero, it appears that at this moment in cosmic time, Earth is not in the crosshairs of any nearby supernova candidates. We can be grateful for the margins the cosmos has given us. We live bathed in the gentle radiation of a stable, middle-aged star, far from the volatile furnaces that would endanger us. Even so, the concept of supernova threats has spurred some interesting science. For instance, astronomers have surveyed the sky for traces of past supernovae and keep tabs on the massive stars within a few hundred light-years. We are effectively monitoring the environment of our solar neighborhood for potential supernova weather. It's sobering to think that events light-years away can influence life on a planet, but it's also part of the dynamic nature of the universe. Human civilization might someday have detectors that could provide an early warning if a nearby star's core collapses. We already have neutrino detectors that would give us a few hours' notice of a supernova. Neutrinos escape the collapsing core before the light from the explosion gets out. Thankfully, the notice will likely be for an